Welcome back to the stream. Sorry this is starting a little later than I expected. Wake up, computer. Hey, Tuco. All right. So, let's make sure that I've got all the chat up and all the recorders going. I think I still need to experiment with putting the chat up inside the stream because that would be interesting. But it also seems like the computer running the stream is still struggling a little bit. But here we go. I think we got that going. I've got my tea. So it's not like I need excuses, but I think the excuse for starting late was helping my neighbor with her computer. It's one of those funny things because like she was, she was kind of expecting that she was doing this thing that was just totally, like I think she was expecting that it was kind of like out of her league of understanding and all that or something, but really it was just she was having a problem that I'd actually had to, where like it was like a new iPad, and then during the setup she managed to like lock herself out, and then so we went through the kind of USB DFU firmware update procedure together. So anyway, that was fun. But now we're back to the stream, and I would set up Tuco Cam. He seems to be meandering around the shop a little bit first. But anyway, today's agenda. So for the second stream today, earlier today, got to finish this little doodad, the Boldport Club Project 3 cordwood kit. So now this is something that works more. This is something that's more a part of a longer-term kind of video project. Just realizing that I think I cut some pieces out of this anti-static bag. Okay, so you may remember from a previous video, I have these Wacom tablets that I've extracted the firmware from using a glitching technique. And so these are both wired up for that glitching setup. And part of where I was going with that video, which I've already published some of these results in POC or GTFO, but I want to do a video on them too, where I take these graphics tablets and I get them communicating with RFID cards. So the way I did that was via this return-oriented programming technique. So I found a way to insert whatever I wanted into the RAM of one of these tablets. But in order for that to be really meaningful, to kind of like craft little programs inside the stack space of the firmware, I had to know exactly what the firmware was running in the device. And so you can't extract it using like the debug port or anything. There aren't firmware updates online. So I had this video about using voltage glitching to convert one of the USB commands into a kind of ad hoc firmware download by glitching it at just the right spot. So the next step in that, I'm planning on doing a couple more videos related to that same project. So I did a video on just getting the firmware out, but having the firmware, the next couple of steps involve understanding the firmware and then developing a way of using the Wacom tablet as an RFID card reader. And then so I ended up doing that by kind of implanting a little program in the firmware using return-oriented programming. So I kind of set up a very special stack frame in the stack memory of the program that was running on the tablet. And then by letting that stack run, kind of, it would sort of like, as you try to return from a subroutine into its parent function, by decoding the parent, address and register contents off the stack, then you can kind of hijack that process and use that for executing your own code by kind of linking together a lot of code fragments via this technique that's popularly called return-oriented programming. So I want to do a video on that because that's pretty fun. And so I used that technique to give the tablet a little program that would change the frequency that it transmitted at to match these low-frequency RFID tags, and then return enough information that I could use some algorithms running on the kind of computer side to decode the tags. But the first step on the way, besides what I've already published on video, which was just tearing down the tablet and getting the firmware out, the next step is just understanding the firmware. And for a lot of processors, this would just be a matter of, like, if this was an ARM chip, you would just load this into any ARM disassembler, like IDA. But this is an opportunity to demo what the technique might be like when you don't have good tools for the processor. So ARM is super common, but these tablets don't use ARM. They use this processor that I mentioned in some previous videos a bit, but it's like an 8-bit processor that was originally designed by Sanyo and then sold to onsemi, and then they market it. So architecturally, it looks a lot like the 8. It's a lot like an 8051, kind of an old school 8-bit architecture that Intel created and that everybody else ripped off. But this is designed for Japanese rice cookers or something, and so you can't just use. Nobody's written like an IDA plugin that can decode the machine code for these chips, but there's a set of tools that you can download from Sanyo/onsemi for working with these chips, but it's really minimal. There's like a third-party compiler. There's a little bit of documentation. I eventually found some documentation on the actual instruction encoding, so I could have written my own disassembler. But for a while, I hadn't even found that. That was like buried in some application note that I hadn't seen. And so the best route to understand the firmware that I'd found at the time was to take this tool that I found on their website, which was like an interactive debugger. So you would attach it to one of these chips live through this USB device, and then use it to inspect memory and disassemble code and single step and all of those things that you want to do with a debugger. But I looked around and I couldn't find one of these debuggers, so the next step really was ended up being to try to get that debugger software to kind of work a little bit without actually having one of those debugger dongles handy. So that debugger dongle was called this Sanyo. The documentation I found called it a TCB87 type C, which kind of conjures like images of giant robots or something. But in this case, I think that was TCB was target control board, which kind of fit into their debugger terminology. And then the type C referred to the actual serial interface it used, and this being their presumably third-ish iteration, it used a one-wire serial bus. So one of my investigations actually involved trying to figure out what that one-wire serial bus was electrically and trying to talk directly to these chips, but that didn't really lead anywhere. I tried generating some waveforms that might have been plausible, like ones and zeros, and oh, hey Tuco. I guess you found the keyboard. Great, thanks Tuke. But yeah, that didn't really lead anywhere. So and then I found the firmware, actually. I found, so in that package, which is probably where we'll start this stream, is just getting into that package that you can download from Sanyo/onsemi. That had the firmware for that TCB87 type C. And so I even got so far as trying to reverse engineer that firmware once I guess that's skipping ahead, but once I had a way of disassembling it, I looked at that to try to figure out the protocol. But it was actually, like, that dongle is actually using some kind of bit of custom silicon they embedded in the microcontroller to speak the one-wire protocol. So just looking at the firmware didn't give me many hints as far as what the protocol might have looked like, so I was still just guessing. Yeah, I was kind of surprised that this LC87 wasn't just something like an 8051. When I first saw the firmware, or when I first kind of got some hints about what the architecture was, because the 8051 is kind of interesting because it has all these tiny different bits of memory. Like it has like a 256 bytes memory area internally that is sort of like a register file, but is also sort of like RAM. And then you can access it in different 128 byte halves. But then there's also external RAM, which is enormous. It's like 16K on a lot of processors. It's like a 64K address space. I think Tuco's over here now, so maybe I can get a better camera on him. I think we need the Tuco cam and a computer. We can get a VM fired up and look at the software. That's where Tuke's hanging out right now. Oh yeah, there's a comment in the chat that custom silicon seems really extravagant for a debug interface, and that's exactly what I would have thought. Like, for most of my reverse engineering effort on that, I was assuming that that bit of hardware was some other kind of general purpose serial interface that they were kind of misusing for this purpose. But the more I looked at it, the more it looked like it was purpose built. And so it might just be that their debug interface is based on some other protocol that I'm not familiar with. They already had silicon for. But it was definitely it was the sort of thing where there were registers where it's like, oh yeah, these just control like the clock rate of the protocol that totally matches what we're seeing on the scope. And these registers are like FIFOs with the commands that go in and out. And like, it seemed like they weren't doing anything super weird at that level. Oh yeah, the other bit of kit here. Let me actually see if I can get the top off of this so we can look at the chip. So I think besides looking at the actual software that we're trying to kind of remote control here, I wanted to reproduce the existing working experiment that I had, which is just using this great FET microcontroller and a terrible, horrendous patch. But that'll just be like a good baseline to make sure that the next steps are working properly. I'm trying to get the top off of this so I can show you the chip underneath. Oh geez, it bent a couple of pins. I can bend those back. Oh man, I hate these really, really wide 0.1-inch headers that have so many pins. I'll bend these mostly into place so they don't get damaged further. I might have to fine tune these later. Anyway, let's go to the DSLR. I already formatted that. Wake up, camera. Sometimes I've got to unplug the HDMI and plug it back in. Yeah, that's better. Great. Alright, so this was my, this was the first platform that I used for this particular experiment. Oh, I don't have it on autofocus. Yeah, so this is an ARM LPC 4330. It's pretty fast. I think this one's like 230 megahertz. And this is a project that's kind of an ongoing hardware project from Michael Osman called the Great FET. And so I've got kind of a prototype board here. And some of the inspiration here was because it has these two USB interfaces, you can program it to be kind of a remote control USB device where you use this interface to program this and kind of talk to it for debugging or for kind of getting data in and out. And then this USB interface can be programmed to be kind of a scriptable device to do whatever you like. And in that way, it's kind of an evolution of the Facedancer platform that we were working on before. Grab that board just so we have that for reference. So we have these boards. This is one that I put together on an earlier stream. This is the Facedancer 21 milled and assembled on camera with a couple of mistakes and reworks. And this is the same design, but professionally manufactured and assembled and everything. But otherwise the same thing. And so this is just an older project, but with kind of more mature software stack, which lets you kind of emulate a USB device on this end. So this, it can choose to emulate either a device or it can emulate a host, and then you can plug a device into it. And that runs on this Maxim chip, which is kind of a programmable USB interface that you talk to over SPI. And then this port is always a serial interface via this FTDI chip. And then you just use that as kind of a programming and kind of runtime and communication interface to this microcontroller. And then usually most of the program that you're actually developing is Python code running on a PC that's attached to this port. And then this is just kind of a remote control contraption that's like operating this USB port to do whatever you want. So it's helpful. It's still really useful. It has a lot of fairly mature software for it, but it's also slow. Oops. And part of the appeal here is that you're not going over that SPI bus. It's actually, despite it being kind of smaller and more modern looking, it's also actually simpler because you just have this one chip doing all the work. So I started here because it was interesting and because it was newer and I wanted to give it a shot. But the software framework isn't really fleshed out, so there isn't really like a place to plug in your own USB device implementation. So I just ended up kind of having to patch the usual firmware for this. So that said, it's messy and I want to replace it with something that actually uses this older but more stable board that we can demo more easily. But the first thing is I just want to reproduce that earlier experiment. And I don't actually remember whether that experiment, whether it needs Linux to compile or whether I can compile it on Mac OS. But let's see if it compiles on Mac OS, because that would be a little bit easier, because that's what my demo machine is. But if we run into snags there, I've got a Linux VM handy that we can switch to. Oh man, that's Tuco, and he wants to play Bolt. Let's see what he's thinking. It's a good glamour shot of this board, though. Hey, Tuco. For anybody who's new to this situation, I have this weird cat that's kind of addicted to playing fetch with these nylon bolts. He's super weird, but I love him. So, these things, 1/4 I think they're 1/4 inch long. I originally got a lot of them for some art project ages ago, and when I moved into this building, my stuff was in disarray, and Tuco found these and really enjoys fetching them. Hey, little cat. Actually, if he's in this mood, maybe we can take a quick sort of fetch break here. Here we go. Hey, Tuco. And I can catch up on chat. Looks like a lot of stuff has been going by on there. Oh, and it's ankle time. Hey, Tuco. Oh yeah, Great Fets. There's some questions about the status of the Great Fet project in chat. And yeah, I don't think you can buy them assembled yet. They're still kind of alpha status. I got mine because Michael Osman was generous enough to send it to me. But I think, oh, sorry, Tuco. And the designs are out there, so you can order the bare boards from Oshpark and assemble them yourself if you're so inclined. And right now, the way I understand it, the hardware is actually pretty well advanced. You can get, like, you can assemble the Great Fet, and there are a lot of add-ons in development for it that people have been doing. But the software stack isn't really as fleshed out as the like the original GoodFet software has become over the years. And I think so. There's a repository for the firmware that we'll actually get into pretty momentarily, and it's like GreatFet-experimental from Dominic GS. which is good, but it's still kind of like not really clear what direction the firmware is actually going to take in the long term. Oh, there's a water bottle on that table. Oh, there's some questions about what bolts Tuco prefers. So, I think currently he's actually kind of a little soured on the 3D printed bolts, and he's been really into the original nylon ones from McMaster. I think maybe the problem is I had a batch of PLA bolts that were printed with kind of suboptimal settings on my little Delta printer, and they had a couple of problems. There wasn't a great texture, so they might not have felt great in his mouth, and a lot of them had problems with the hex head and the shaft of the bolt separating because there wasn't a strong join between layers. So I think he's gotten a little suspicious of the 3D printed bolts in general, and he's been like intentionally seeking out these nylon ones. So I don't know what to do about that. I think I might have to try to up my game and like really get rid of all the really bad 3D printed bolts and print some good ones and see if he likes those. But yeah, this is nylon off-white with a pretty good texture. Like I bet it has a great mouthfeel, Tuco. Isn't that going to be awesome in your mouth? Yeah, check that out. He's also pretty into these carpet squares. Good job, Tuke. Yeah, pets are really nice. Tuco is by far the best roommate I've had. Yeah, I was going pretty deep into roommate feels on the early morning stream on account of the, I don't know, some of you might have heard, but there was a pretty bad structure fire that ended up killing, I think, like 30 people, like right near here in Oakland, and it's still been on my mind because it's one of those things that I was afraid of fire a lot as a kid, but I've gotten more pragmatic as I've gotten older, and I try to be safe about stuff and have a decent amount of prevention, but try to not let fear rule my life. But the warehouse that caught fire and ended up killing a bunch of people during this concert is a lot like this place I used to live before I got this concrete box. Oh man, good old cat. Well, not old, he's actually pretty young. He and I met when he was like only a little over a year old. I think now he's maybe about 3 years old. Oh, he's got some lint attached to this bolt. Hey, Tuco, you don't want lint, do you? No more lint, just bolts. Yeah, Tuco and I have got a pretty good bond. I feel like we've been through all this shit together because I don't know, that place that I have all those crazy feelings about that reminds me a little bit of the warehouse that had the tragedy there recently, like that. I don't know, like all of those feelings are also kind of tied up with Tuco because that's part of the reason I ended up with Tuco, but I also feel like Tuco and I kind of rescued each other from that. He's really good at finding these bolts when they go. Like, I really need more of a, for these Tuco bolt chasing sessions, maybe I actually need more of like an aerial camera that can show the top-down view of the shop. I mean, ideally, I would have a camera that could actually follow the cat around. Ideally, not with, like a drone or something that would just freak him out, but with something like computational involving a bunch of cameras and sensors. Hey, Tuco, nice kick. Oh, so actually, while Tuco's fetching, I have another thingy that might show well on the camera. So something I was experimenting with this morning. Oh, maybe it's just not going to show up. Yeah, I might have to save this for the desk camera. But I was experimenting with mixing, like having a design that uses both 3D printed parts and polymer clay. And if you're not familiar with polymer clay, it's basically stuff that you can model like clay, and then you bake it, and then it acts like ceramic. And then the way they actually accomplish that is that it's a suspension of little plastic particles combined with some kind of like oily binder. And then as you bake it, the binder evaporates off, and you end up with just like a hard plastic left over. And it's interesting because you can like knead in different pigments and stuff into it. And then you end up with something that's actually pretty solid and feels nice. There's definitely some warping. You can probably see that. But it's not awful for this design. But in general, I was thinking of ways to cut down on that, possibly by either sandwiching this between some other layers while it bakes, or maybe there's a different temperature that helps, but or possibly by 3D printing the design with a tiny brim attached with multiple pieces and then like a square frame, and then you just bake that whole unit and then separate out all the individual things. Oh, Tuco knows I'm distracted. Hey Tuco, where's the bolt? Hey Tuco, where's the bolt? Help me find it. I'm not as good at this as you are. Do you want to fetch a scanline token? Do you find this interesting? Well, he's chasing it. I don't know if he's going to bring it back. No, he left it alone. I would throw a bolt, but I don't know where it went. Hey, little critter. All right. Well, I've actually got to. You might notice this water bottle and the tea. I might actually have to go use the restroom momentarily, but I will be back, and then we should end this little. Oh, you can also see my loft up there. I don't know if I've showed that off yet. That is where I hang out when I'm not in my shop or outside. But yeah, then let's get into taking a look at this this weird debugger software and what we can do to kind of give it the USB device it's looking for. computer recorder is already running. Hey Tuco, you still hanging out? Where is Tuco? Oh, there's the kitty. There's the remote. Alright, now we have cat cam and all the other cams and the computer. I don't need this to keep rolling. Oh, Tuco, do you still want to play? Am I abandoning your playtime too early? Yeah, okay, fine. Whoops. That was a weird throw. You're gonna bring it back to me anyway? Thank you. You're so good at that. Alright, maybe we can get this. I think I've already got a VM set up on this machine that has the Sanyo on semi software going. So let's take a look at that. I think it's in here. There's already an upgrade? Alright, fine. Hey, Tuco. Where'd the bolt go? Where'd the bolt go, little guy? I don't see where you put it. Oh, there it is. He always stands in front of the bolt, so I can't see it. He doesn't know that he's so much better at seeing the bolt than I am. He has much better night vision. Thank you. Oh, you kicked it way over here. Here it is. Restoring the VM. The most exciting part of every stream. Copying data from hard disk into RAM. Ooh, yeah. There's a suggestion from the chat to have a bolt thrower that can be fired from the chat. This is actually a long-time goal of mine to have some way of facilitating more interaction between Tuco and the internet crowd. Yeah, I've got a prototype around here. I was working on this 3D printable wheel that you could spin up with like a CD-ROM motor kind of thing, and it had these little kind of flexible fins that would catch the bolt and fling it. And it was all right, but I don't think it goes quite as far as he would like it to go, so I think I might need to do another design based on like two wheels that like pinch a bolt and like fling it forward, kind of like a tennis ball thrower. Oh, we got some graphics glitches here. This looks like the texture is smaller than the renderer thinks the texture should be, and it has clamping on the edges. So OpenGL is rendering it with clamping, and then on the next frame it'll be fine, but this is like a frame that nobody thought about, and the frame is very slow because the hard disk is swapping or something. I can stop having that be messagey. Oh yeah, good suggestion for another bolt thrower design with like a pinball kind of like slingshot that you pull back. That would be good too. Yeah, if somehow I got myself suckered into thinking about mostly designs that would be where like all the interesting active parts were mostly 3D printable, but something where you have a spring storing energy could really do a lot of good. So man, I don't know whether that's something where I should be looking for just like random springs online, or whether I should try to make a spring for that. I've got some spring steel. Oh, there's also a question in chat about this picture that's on the VM's desktop wallpaper. This is a photograph from inside of a weird art installation. This was actually, these are all pieces of cast glass, and this was inside of a room that was itself inside of like a little like RV, like a camper vehicle, like a trailer. And then that was just out in the desert, like really, really far out. So it was part of a series of art installations that were out in the desert called High Desert Test Sites. And so I went there years ago with some friends, and this was one of those installations where from the outside it just looks like this dusty trailer, and then you go inside and it's this white walled space, like a white cube, with, I think there were like some white beanbag chairs or something comfy to sit on, and then all these bits of cast glass, and the shapes they were cast from looked like industrial tubing and stuff like that, like dryer hoses and whatever, and elbow joints. But then the glass itself was just subtly colored, and then there were systems of holes and reflectors and stuff that allowed the sunlight from outside the camper into this weird space. It was super weird. It was super strange, but it was enjoyable. I think this might even be the same VM that I already installed that software on. Oh, so I installed some STM32. Oh, there's a bunch of stuff on here. This VM sure is choppy. It's probably paging in all sorts of stuff. Oh, there it is. LC87 series development tools. So yeah, these are the ones that I installed from Sanyo/OnSemi. There isn't a lot here. Like, I think actually the compiler isn't even here because the compiler is like a separate thing that they licensed from someone. Let me see if I can zoom in actually. So that's what's in the start menu. Not so interesting. What do they mean by training kit? And I think Easy Micon is some brand name that originally meant something like a microcontroller that's easy to use, but I don't know what it means in this context. Anyway, the thing we actually care about is this RD87 on-chip debugger. So that's what we're going to go into, but I'm actually kind of curious if this has any worthwhile documentation. But maybe this VM just needs to like page everything in. So maybe I should play with Tuco while I'm paging in the entire universe off of the disk. This demo machine has one of those, it's not like actually an SSD, it's just a, hey Tuco. It's just a mechanical disk with a bunch of cache that Apple invented a new name for. Hey Tuco, where's the bolt? I don't see it, little tiger. Are you sitting near it? Are you covering up the bolt? Oh, here it is. So also, he seems to really be into these bolts that have a color that blends in. I don't know if he would be as into like a nylon bolt that's made out of like black nylon, because if it still bounces the way he likes, it would certainly be way easier for me to see. But I think maybe part of why he likes these is that they're kind of hard to see. Hey, boy. Yeah, he just really wants to follow this when I throw it. You gonna do it? Oh, he thinks I already throwed it, but I didn't. Hey, Tuco. It's still over here. All right, Tuke. Oh, this Easy Micon directory is just a link to their sample software, which is not super helpful. I think this is even using a compiler that I don't have installed, like, because it comes with some other trial thing. Hey, Tuco, where'd the bolt go this time? Oh, here it is. I'm so disappointed with like anytime you get software from the silicon vendor, you know, whoever makes the chip, they're just usually so terrible at software. And you know, sometimes there are exceptions, but the vast majority of stuff that you download, like as part of the official board support packages, is just, you know, like it's good to have that stuff as a working example of how stuff can be done, but I usually don't want to use it any more than I have to. He thinks it's in the hammock. I don't know if it actually is. He'll get up in there and try to get the bolt out of it. if he thinks the bolt is in the hammock. Hey, Tico. Oh, there's a question in the chat about the equipment, because it's a little, the setup is a little weird here, but yeah, there's like a Mac Mini that I have hooked up as kind of a demo machine here, but there's also, there's a couple of Windows machines and another Mac. There's a variety of hardware running this show. Oops. He thinks it's in there again. All right. Autofocus. Do some focus, please. Hey, Tuco, do you know how to make the autofocus work? I think this worked last time. Yeah. This one is not like a fancy camera. This is just like a webcam. I was originally trying to use one of the Logitech C9 whatevers, the popular, cheaper Logitech HD cameras. I was trying to use one of those as cat cam, but, and that's what I have as the desk camera here, but it was having trouble focusing close up, so then I tried this one, which is like a Microsoft Life Cam, which seems to have a better range of autofocus, but then sometimes the autofocus gets stuck. Excuse me. Okay. Let's see if we can start parallelizing this cat experience. Not just the computer and the other stuff. So yeah, these are like the sample programs. It's got like pre-compiled hex files and stuff. Oh, shit, I think I might have hit that mouse bug that I've already hit a couple times in the screen. If I'm zoomed in, I have to make sure that Synergy is turned off or my mouse might get stuck. Alright, so yeah, these are just some kind of basic examples. I think I looked through these before and there wasn't anything super interesting. The most interesting examples would be something that includes their USB stack, because then that might have clues as to how, if like we're glitching USB code in this microcontroller, then it's likely that whatever USB code in the firmware we're glitching, it's likely that was copied from some example from somewhere. So the 871 is the model with USB, but this still doesn't look like anything USB related, so I don't think I found the USB sample code in here. But anyway, being in the file explorer is actually kind of where we want. So actually, let's go back. How did I even imply that I wanted a shortcut? Hey, Tuco. Where was that thing? That was like LC something or other. Or is it Sanyo something? There it is. Sanyo LC87 is what we want. So, okay, fuck easy Micon, I don't need that. Project, what is in there? Sample projects. Okay, so this might be useful. So RD87 is that debugger we're interested in, and these seem to be model numbers that are specific to each chip. So just out of curiosity, let's pick one of these. How far down do these go? Any 871s? Because I think there was a directory in here with, okay, these are like template projects. So if you have this chip, you want to start a new program, you copy and paste this thing. There's another directory in here. I remember having configuration files for the debugger that were per chip. And those actually proved useful because I was able to extract register addresses from those that I could use in disassembly later. Alright, so we don't care about those. What about doc? We have language choice, that's nice. So this is the file where it taunts me with the existence of this TCP87 Type-C dongle that I don't know where to get, but all of the software is designed to use the TCP87. Hey Tuco, you really want me to throw this? This one? Oh, I dropped it. Tuke. Little cat loves his bolts. Yeah, so I mean, there's some information here. Like we can tell that, like some of the stuff. If you were here like really early in the stream, I was kind of giving some background information on this thing that I want to emulate using the Facedancer. So that's this TCP87 Type-C dongle. I couldn't find anywhere to buy this thing. There was one developer kit I could find for this LC87 chip, and I bought it. I don't even feel like bringing it out for the stream right now because it's so pathetic. I might bring it out for another stream, but it's like it doesn't even give you the ability to like download code to this chip. It's like an eval board that's pre-programmed with some USB device examples, and then they give you this CD, and it doesn't have development tools. It has some Windows programs that talk over USB to their examples. So it's really no more useful for development than one of those tablets that I've hacked up is. So far I haven't found anywhere where you can actually buy one of these TCP87 debug dongles. And so Type-C seems to indicate that it's the one-wire version rather than the three-wire version. And so I've gone through these documents in the past, and there's stuff like this that's like documents about how to use, is my VM froze again? There's like documents about how to use this stuff, but like they don't document the actual serial protocol that the debugger dongle speaks. There's a quick start. I mean, this is probably going to rely on a bunch of stuff that I can't get also. Like this kit that we're going through, I forget exactly where I downloaded it, but it was just somewhere on like Sanyo's website. So I found the site for this particular kit, or this particular product or processor line, and it was in there. So yeah, there's this trial kit that, I mean, this is probably just really obsolete. This is probably just stuff where, you know, it used to be you would just get this dev kit on CD when you wrote in to request it, and nowadays the distribution channels and everything like that are different, and you just don't get copies of this stuff anymore. This is the program we're interested in, though, this on-chip debugger. And so the reason I'm interested in this is when you connect it to a target, it'll actually give you a disassembly window. So I guess it isn't even this. This looks like source since it has comments. But it'll actually, when you connect to a target, take the binary code in memory and convert it back into instructions, which was super useful when I didn't have any documentation about what the instruction format was. Hey, Tuco. Brief manual. How brief is the brief manual? Hey, Tuco, do you have a bolt for me? Yeah, this tasking C compiler is the third-party thing that you're supposed to use to compile the examples, but isn't actually included in this package. This is another thing that bugs me when silicon vendors are like, I have this great chip, but instead of telling you how to write code for this chip at a fundamental level, I'm just going to tell you who you can buy the compiler from. And I hate that. It's like, I mean, it's very common now. Like, you'll find all sorts of peripheral chips where you buy a driver for it for Windows or something, and you get a data sheet that tells you electrically the care and feeding of this chip, but you don't actually get a full register interface for it. So this is talking about how to use these tools. This doesn't seem amazingly interesting. Like how to invoke the linker. They're talking about tape out here. I've seen some of these references around the documentation that make it seem like this tool chain is really geared toward projects where they want to target mask ROM. So, you know, they have both flash and mask ROM versions of a lot of these parts, but A lot of the documentation is like, here's the process you're going through in order to get your chip to the fab, assuming that the mask ROM is your actual end goal. Hey Tuco, you have a bulb, don't you? I don't see it. Tuco, why do you hide these things from me? Where's the bolt, little guy? Are you sitting on it? Or am I just not seeing it? I don't know where my cat is leaving these things, but I will keep an eye out for that. Alright, so RD87, that is this thing that I want to figure out. So bin, what are these? This is, I think, something related to their example code. I don't think that was important, but we can come back to that if it is. I think debugger is what we want. So, yeah. So we have some configuration settings, which are text. Text is always nice because it's easy to read. There's an auto-exec thing. This is not especially interesting yet, though. We have HTML documentation, which is the most secure documentation format we all know. And I think I've gone through this before, and it was kind of interesting. Not immediately helpful, but certainly interesting. Oh, is it under the chair? There's a helpful comment in chat. No, clearly I need to make some... Oh, here it is. It's like way back here. Hey, Tuco. Yeah, so we've got this whole system for the onsemi LC87 microcontroller system. Oh, where's my mouse? Man, so many things play badly with the screen zooming. Like, I was having trouble with screen zooming plus Synergy, which is the program I use to remote control the streaming computer from this one. And it also seems to occasionally have bad interactions with the VM. So this was actually pretty useful, and now that I'm looking at it, I did get into disassembling this RD87 program, which we might end up getting into today also, since that's partly how I figured out like what it's expecting as far as, so it wants this TCB87 thing. What does it want it to do? Well, one way to figure it out is to disassemble this program and figure out how it's trying to talk to the TCB87. But that's not necessarily the first step. I think the first step is to look at how this is actually connecting to the outside world to see like even what kind of USB device it's expecting. But this was kind of a useful little kind of Rosetta Stone for understanding the commands in the debugger. If you've used other command line debuggers like GDB or WinDebug or LLDB, this is kind of similar, but of course they've got their own flavor of commands. But this makes an interesting way of understanding the actual binary because, text is easy to pick out amongst a bunch of other like stuff that is not text in a big binary file. So if you can find, trying to find some actual text commands in here. Yeah, so there's stuff like this where there's a command line in the debugger, and this like writes some data to a particular kind of RAM, which is something that's important on this microcontroller. And but if you see this string exm, you'll probably find a table somewhere that has a bunch of strings that are like, this is the command, this is the function pointer to the code that handles it, and then you have a way of understanding that function that's for this command that's documented is manipulating these data structures, and now based on the documentation for the command, now I understand more about what those data structures are. So this stuff ends up being pretty useful. And then here we have the program itself. Here we go. I think in addition to the actual program, this had just a bunch of these configuration files. I think these are the files that I mentioned earlier that I was able to extract just like register locations from. But normally these are used as part of the initialization of this application. And so this is the app. This is what actually knows how to disassemble the code for this unknown microcontroller. So one way of proceeding would have just been to disassemble this RD87 program, find the functions inside it that are responsible for doing the disassembly, and then just kind of extract those or kind of call them in isolation. I looked into that really briefly, but it didn't seem like that would actually be easier than emulating the TCB87 device. But then this stuff is fun. Can I make those? Yeah. So these, you can see by the size, oops, let's go back down. These hex files are, not insignificant, like hundreds of kilobytes of code. And these are named according to the debug dongles. So I ended up finding out that I think TCB87 might be their original version, and this might have been a later revision for their kind of A and B protocols that were still 3-wire. But then, and also this first one has a much earlier timestamp, which is interesting. But then this one, TCB87W, I forget exactly where I saw this particular hint. I think it might have been in the disassembly of this RD87 application, but I noticed how it was using this particular file, and it seemed to be related to the 1-wire protocol. So I think the W is for 1-wire, and I think 871, that's the model number for the particular series of microcontrollers in the tablets, the one that has USB. So I think that might have just been that they added that new debug protocol with the LC871 generation, and that they, correspondingly with that, have a new firmware for the TCB87 dongle. So this is what I was disassembling later to see if this had any clues as to the debug protocol. And it turns out this, it's a bit of a chicken and egg situation, but if you could disassemble this firmware, you would know how to emulate this device so that you could pretend to be it and then run this RD87 program. But without knowing how to disassemble this particular processor architecture, because they're using the same architecture for the debug dongle as the microcontroller itself is, without having a way of disassembling this code, though, we're kind of stuck with just looking at the context. What is this program expecting? So we might get into the binary here. The first thing that we can see, though, is that it's got a driver that it's installing. If we go up a level. Hey, Tuco, where's the kitty? Oh, Tuco's in the chair here. There we go. I think Tuco might be appreciating the heater. It might be that time of the night. All right, so the first thing we can do is just check this to see what driver this is. Like what the, this might tell me what the vendor is of the particular, oh geez, my mouse. Okay. I don't even know if this will be better with the, I was thinking about full screening this VM and then maybe using the zoom in Windows. Oh, there it goes. It was just taking a while to load. All that memory is paging in. All right. Oh, now I've got this. No, that's not better. That's not better. It's just slow, and I have this magnifying glass. It's acting a little bit like my mouse is just suffering from some wireless interference. Might move the receiver closer. Anyway, if we have a driver here, without even taking a look at the code, we can look at the INF file to see what it's installing and what this driver is claiming to be responsible for. And so that tells us right here, we've got the vendor ID and product ID of the USB device. So if we want to start pretending to be a USB device, the first thing we could do is just be some generic USB thing with this identity and let this driver attach to it and see what happens. And this is mostly just information about the device. You know, there's some branding here. It's hard to tell whether this, you know, one of the first things I look for in a USB driver is this driver actually going to have any interesting code in it, or is it just like a forwarding service? Because usually the way these things work is you make the hardware, and then you don't want to have anything to do with writing kernel drivers. You just want to write like a regular C++ application or Visual Basic or whatever you program in, and you don't want to have to write a kernel module. So you buy or find an open source thing, or you somehow acquire a kernel mode driver that you can customize very slightly so that it'll install on your device, but it's actually generic under the hood. And so that's kind of what you first want to look for signs of. And I think in this case, this is actually a pretty generic driver. So this file was probably generated by some kind of tool automatically. But for starters, the sys files are pretty small. That doesn't tell you everything, but let's actually, do I have IDA installed? I think I do. So let's take a look at the driver and just see, like, is it all glue code? What are the strings in there? Does it have anything that we actually need to pay attention to, or is it just like connecting the user space program to the kernel module? Oh, did I mess up my Python install? All right. Actually, let's take its advice and drag the file there to disassemble. So you could use a number of tools for this first step. I'm using IDA because I have it handy, but really for this, just determining what driver this really is, you could probably even just use strings. There's a PDB file, sure. Yeah, let's keep waiting. This is interesting. There we go. Yeah, I somehow hosed something in IDA Python. I'll have to take a look at that. Anyway. Well, that answers our question pretty quickly. If we look at the strings, so all of these indicate so this is a common programming practice if you haven't encountered it in kind of lower level compiled languages like C, that a lot of the time you'll instead of like having exceptions and things, you'll just prefix your errors with like a module name and then just like call a generic panic function or something. So right away we can tell that somebody thinks that this module is a universal USB driver. And if we look up here, it's storing some data in the registry with this key. And we can see that it's something originally made by this soft design company, and it's probably a product. If we Googled this, we could probably see, we could probably see like who's selling this as kind of a middleware device. And then all of this stuff that's going on, these are the kinds of error messages that you would have if you were writing a driver that was just kind of attaching USB stuff to other stuff. Yeah, we can see and this data here, these are actually in the file's resources, so this stuff would actually just show up if you right-click the driver and go to Properties. You wouldn't even have to disassemble it to get this data, this stuff right here. Okay, so this is not interesting. actually have to take another quick break, but I will be right back, and Tuco will keep you company in the meantime. And then I think let's take a look at RD87 quickly to get some context there. And then we can actually go about reproducing some of these experiments. Hey Kat, thanks for keeping the stream warm. Alright. So, let's get out of this driver. Let's get into something more interesting. So RD87, back in here, in this land of twisty little config files. Oh man, the scroll direction always throws me for a loop. Here we go. So, I apologize for the low resolution of this computer on the stream. I've been trying to get it, it's kind of limited by the CPU on my streaming machine right now. But I will try to zoom in and get a good shot when I'm doing something interesting. So back to IDA. Let's take a quick look at RD87. Alright, so this is just the usual. It's asking us what kind of binary this is and how to analyze it. Oh, yeah. Alright, so it is starting to analyze stuff. So there's a lot of ways to proceed here in terms of, so IDA itself is trying to automatically analyze, plus there's probably a lot we could look for in terms of strings and following imports and exports. If we're interested in kind of emulating the debug interface, the first thing to look at would be to try to find the functions that that actually interface with that driver that we were just looking at. And so that's probably going to be something that speaks through an I/O control. So the first step is probably imports, and look for this function called device I/O control. There it is. So that was a list of all the functions that this program looks for in external shared library files. And then if we click on that cross-reference, it takes us to this entry, which represents the actual kind of imported address of this function. And then we can see cross-references to this location, which might still be work in progress because I think IDA is still loading this file. I'm going to take the mouse receiver and plug it in up here, because I think my mouse is losing packets. The fans in the computers are going. Is it mouse time? Is it? Oh, now it's mouse time. I think my VM is just not the highest performance thing ever right now. Don't know if there's something else running in here or if it's just not the greatest configuration. Anyway, lots of imports. Where were we? Device I/O control, right? We want this. And of course, the nicest thing about an actual reverse engineering tool like IDA versus just a plain disassembler is that it'll have cross-references like this. So interestingly enough, it looks like they've got their own wrapper around device I/O control, and there's just this one function that's actually calling it. So we've only got this one place to look. And if we look at the flow control graph, we can see kind of what's going on. There's an I/O control up here. And this might be something where there's like one I/O control for initiating the transfer and then another I/O control for data. But so there's, oh, come on, scroll. Oh yeah, there's plenty of strings here documenting what's going on. So we can see as it goes through here, you know, if it hits this path, it's giving us a nice error message telling us something failed there. So it is nice when the code has this much debugging built in. You can use this to get some good hints as far as where, you know, like instead of, for this example, instead of like necessarily looking at the loops to find out, you know, looking earlier to find out where the input and output data is, you could just look at this because this is a debug print that's like hex dumping the data. So this function here is probably some kind of debug printf, and you see it in a bunch of places. So we could rename that. Something like that. Call it RD87 debug print. Just make up names. And then, oh man, I totally don't know what's going on with this mouse thing where I occasionally just lose control of the input, but it is annoying. I guess I've got to ungrab from the VM and then regrab. Anyway, so if we look at this loop down here, we should be able to see that like this right here is probably that byte. So this is x86 speak for sign extending an 8-bit number into 32 bits. And so this gives us the address for the data that, that input-output data we're dumping out. So anyway, we could go into this function in more detail and try to figure out, like odds are this is kind of a generic wrapper around a function that does some kind of a USB operation. So we can probably map the inputs and outputs to this function into you know, aspects of the USB spec. Like this probably has a way of saying like what kind of a USB transfer it is, like what endpoint. So this has a this bytes returned thing. Let me zoom in case you can't see that. So IDA is trying to kind of propagate information as much as it can. So this is just a fake name based on the address of the subroutine and, or you know, function. And it knows that it has 3 parameters just because of how the stack is laid out, and it's seen it's seen references to those 3 different addresses, you know, in the calling signature. So in this case, it's 32-bit x86, so those would be coming in on the stack. But it also propagates information. So in this case, bytes returned, it must have propagated that up from something else. So I'm curious where that is. So that's going right to device I/O control. So IDA has a library of stored signatures for, so if you do like an import of one of these standard Windows functions, then IDA will know the arguments for that Windows function, or if it also has ways of noticing functions based on binary signatures. But in this case, this is a standard Windows function, and we can look it up on MSDN and see what's going on. But that's where these numbers come from, and so, or that's where these names come from, and it looks like bytes returned. I mean, so in general, that's a way for the driver via one of these I/O controls. And if you're not familiar with I/O control, it's like if you think of the kind of Unix slash, most modern OSs have this way of interacting with devices on your computer where they look like files. And you can read from the files and write to the files. So if you have a serial port, there's a way of getting something that looks a lot like a file, and you can read or write, but then it's actually sending bytes or reading bytes from the serial port. But that concept has been very, very generalized by every modern OS, and an I/O control is just this other primitive that is something that isn't a read and it isn't a write. It's just this other thing that you can do to a device that you can just do anything you want. So in this case, it's just a great way of just packaging any USB command you want into this other container that then transmits it into the driver, that then lets your driver do anything you want to the USB device. So device I/O control. Normally you would search for Windows API, stuff like this, on MSDN, which is Microsoft's reference, but yeah, for something like this, I would expect the first Google result to just take you to MSDN also. There's lots of different ways of pronouncing this. Somebody was asking in the chat. Yeah, there's, I usually pronounce it I/O control or ioctl. I'm sure it's fine to pronounce it IOCTL, but it isn't. I've probably heard I/O control and ioctl much more often, probably just because they're faster. So let me zoom in here slightly. In this case, bytes returned is just one of these many parameters that is returned by device I/O control. And that's a way for, it's traditionally a way for the driver to tell you how big the transfer was. So if you were to implement something that looked like a read over this, then your in buffer size would be however much memory was available for in buffer. So your program in user space would have this chunk of memory that you've allocated by doing a new object or a malloc or having a stack variable or whatever, and maybe that's 4 kilobytes. So you'd have a 4 kilobyte chunk of memory pointed to here, and you'd have a 4 kilobyte buffer size here, but then, or that could be input and or output, because Windows gives you separate buffers for input and output. That's kind of a difference between the way Windows does I/O controls and Unix-style operating systems. But in either case, you, as the user space programmer, give the kernel a buffer, but then the kernel also has the opportunity of coming back and telling you how much of that buffer it actually needed. So maybe you're like, I want to read up to 4 kilobytes, here's a buffer that can hold that much. And then the kernel's like, great, actually there's only 100 bytes available. But it's unclear, it might be doing that here, it might be using that for something else, like there might be like a wrapper around the actual data that this driver adds. One of the first things to look at so we've established that this function is like the entry point to the USB driver. It's also interesting to look at how it treats time in addition to how it treats memory. So we can see that it looks like it's waiting for a result, so it's blocking. It doesn't have a way of like asynchronously asking the debug dongle, like start doing something and then tell me when you're done. It's just like do that thing and wait until it's done. So it's asking for a result here. This function here, wait for single object. So it looks like what it's doing is it's calling device I/O control in an asynchronous way. It's saying like start that operation here, and then it's making sure that that succeeded, but then right away it's like, okay, let's make sure that that finishes. Let's just ask the kernel to put this process to sleep until the driver finishes that whole USB operation. So I don't imagine this debugger was ever that fast. You know, this is something that you would do that would really simplify the design of other software on top of this, but it doesn't allow you to make any progress kind of while the hardware is working. So you can't do parallelism between the hardware and the software when you write code like this. Looks like it's checking the timeout, and you can see this upward arrow indicates a loop, and so I'm not going to go through all the math here, but it looks like it's calculating whether it's been too long, and it's going back up and running this again if there's more time remaining in the timeout. And then if it's timed out, it can cancel it, or if it succeeded, it can get the result. There's a lot of stuff in here that is a little easier if you're familiar with some of the Windows terminology. Like overlapped is the way Windows talks about I/O operations that can run in the background while your threads operate. And then after that, so it's doing this call to the driver, then it gets response. Now this is what a switch statement turns into. You have the compiler basically gets this puzzle to solve where you have this number going in and a bunch of control flow paths going out, and the compiler gets to figure out how to match those up. And often it's with a lookup table. So this is probably just looking at the error codes. It's probably not super interesting. I really don't know why this is so slow right now. I'm going to have to check out this VM. Usually when I interact with IDA, it isn't this slow. There we go. So it looks like this is just switching on the results from that and, you know, making an error message if it needs to, stuff like that. So the next level up from this is probably going to have something more application specific, and we can start seeing how this is used. But if we need to know like exactly what these arguments are, then we might have to trace through this code to figure out where those go. So in the meantime, I'm just going to rename this like IO control wrapper. And then we can see where this is called. There we go. So this is called in lots of places. So I don't think, last time I did this, I don't think I actually went through all of these, or even close. I think a lot of what I was doing was more runtime driven, like just try it, see what it accesses, and try to get it past that, get to the next point, which is nice. We can spot check these if we feel like, but see if they have interesting text or interesting context nearby. So this is doing something that is reading a big block of data from the device, because near the beginning of the function it's doing this IO control. If it fails, it's returning an error code, but if it succeeds, now it's doing a copy. This stuff down here with the repeated, that rep move SD and rep, come back here. This is not the modifier key I thought I had. Here we go. Okay, these, if I can actually zoom in without this thing breaking. The rep instructions here are basically unrolled mem copies. So that's some kind of buffer. This is cheating by kind of using knowledge from ahead of this in the process, but a lot of what it's doing with this debugger is issuing commands that read and write memory regions in the processor. And so the debugger firmware knows about the protocol that that is spoken on the wire between the dongle and the target processor, but then this debugger program asks the dongle to read and write memory regions on its behalf. So what I would expect to see here is there's the device IO control function, then there's this IO control wrapper around it, and then there's a bunch of functions that call the IO control wrapper that are all doing different kinds of memory operations. So I don't think I'm going to go any further into this, because for something about this setup is making IDA really painful to use, and we don't really need to get any further into this. Here's another one where it's not like a block of memory, but there's a bunch of individual values, so it's the kind of thing where if you need to know what these are, you could trace them. You could just manually, follow these values through. You could run this in a debugger and set some breakpoints around here and just inspect them and see, first of all, when is this code hit, and then if you have a bunch of known values that you have in the system elsewhere, like do you see those here? Can you match them up? That kind of thing. Oh, exit this VM. All right, let's see if we can get some code loaded on the Great FET with the kind of fake TCB87 here. So I think from this point on, I want to be using this VM to run the RD87 program, but I don't really want to be using this for developing stuff. And of course, another option here is instead of using something like the Facedancer at all, because the RD87 program is running in a VM, it would be totally possible to write a simulation of this USB device that runs at the virtual machine monitor layer. Oh man, this wants me to update right now. I'm going to put that off. All right. So if we run this RD87 without any of our special hardware attached, it just gives us this error message. TCB87 not found. So I think we might even be lucky enough to already have the relevant firmware installed on here. So I'm going to first just try plugging that in, and we might not even have to compile this in order to use the reference before we get to re-implementing it. So I don't think I need the host port at all. I'm just going to use the target port and plug that in. And USB hub. Alright, and connect it to the VM. Oh, I'm not seeing the device. It's possible I need to plug in the other port to power this. I forget how the power is set up on this particular board. Let's see if I can get away with plugging both these ports into the same USB hub at first. Alright, oh, that's right. This is an even bigger hack than I remembered. So I didn't actually, part of what's experimental about this firmware is that there isn't really a working library for using this USB 1 target port. So what I ended up doing was I hacked the firmware up so that it becomes the device that I want on this port instead. So that's why VMware is calling it a Sanyo Great FET, because it's noticed the Sanyo vendor ID, but the string says that it's a Great FET. So let's actually just only plug that one in. Alright, we've got our Sanyo Great FET back, and let's be sure to connect it to Windows. Don't want anybody else seeing that. And we should still be able to see it in, I keep going for USB prober, but we should still see it in IO Registry Explorer and in the VM. Do we have IO Registry? What? I think this demo machine might just be like in the middle of an update or something, because that's not normal. I'm just going to look for it in the VM. device manager. Oh, is it device? This is .msc. I used to be able to remember what instance of that was appropriate for each version of Windows I worked on, but there are just too many versions of Windows now. That is not what I wanted, actually. Oh, I want device manager, not devices and printers. Because printers are totally not devices somehow. VMware virtual USB mouse. That's familiar. Okay, so we should see our Sanyo something or other in here. Oh, I don't know why it has a ding next to it. Something is not happy with the Great Fet. But let's see what this is. Okay, I don't know why update driver is grayed out here, but let's see if we can just first do that and then let's maybe just replug this. I don't know why it's not allowing a driver install right now. Oh, Windows is so weird. Let's replug that. Don't know if I tried this in a VM last time. I was using my Windows desktop. But I don't know if it's the VMiness or just this being kind of an old Windows. Got a good old question mark. Devices and printers. That is... Okay, well, maybe it's fine and it's just in the state of not having a driver installed, but I thought that since installing this package it would have already installed this INF file, but maybe let's install it manually. Great. Man, Windows. I might just have to use a different version of Windows for this. But let's try, let me see if I can uninstall this first and then let it reinstall the drivers when I replug it. 'Cause sometimes that helps. It's just very weird that I am, like, there is no driver installed, but I also don't have the opportunity to install a driver. Am I just not running Device Manager as a privileged enough user, maybe? I guess this is, what is this? This is Windows 7. This is before we had to worry about that. I mean, Windows 7 is old. I just had this VM handy. Well, let's replug this. Guys, I don't think I have PowerShell installed on this. This is like Windows 7. I mean, I have newer versions of Windows. Like, all my physical Windows machines run Windows 10. This just happens to be an old VM that I had this stuff installed on. Oh, I think we got it, though. I think this just required some replugging. So I think this is it. This EVA on-chip USB IF driver on microcontroller support tool. This is what the Great Fet is pretending to be. That's our thing. AC31211. Okay, so with that, now we should be able to actually run this RD87 debugger. Oh man, the mouse keeps spazzing out. There we go. And then it opens like instantly. And then we have this pretty old school looking debug console here. So all of this contents of code memory is coming from an image that's just in this patched firmware on the Great FET. So this is just whatever image I wanted to disassemble. In this case, I think this is the tablet firmware. Oh, it eventually... okay, I don't know why... oh. I think I scrolled past the end of the image and maybe my firmware is disagreeing about error conditions. So okay, maybe it's not the most stable thing. Perhaps if I don't scroll down that far it works fine. Oh, maybe I actually crashed this somehow. I probably have a bunch of code in this patch that doesn't check boundaries, and it's quite possible that the wrong request would just crash the firmware. But that's part of why I wanted to convert this to a Facedancer project, because this version of it is terrible. I just want to show it working, because it works, and this is it's good to have a reference point before completely throwing something away to have the old thing working. I can't tell if it failed to register my double click or if it's just launching very slowly. Alright, so you see that, it's got like a jump instruction, and so like a bunch of this stuff will just totally fail. Like if I tell it to single step, or if I read other parts of memory, it'll probably just mess up, but the program is running and it's disassembling this firmware. And from here, all I did is I think I just copied and pasted. I don't know why I'm actually not allowed to copy more than one line right now. I think that just might be my mouse acting weird with these drivers, but through some mechanism which seemed pretty normal at the time, I was able to just copy and paste the code out of this window, basically. Oh, that's what I did. This is like a memory viewer, but there's also a command line. That's what I did. I just used this to dump memory. So this is like your usual debugger command line. And so using those commands that we saw in the help file earlier, I think, yeah, I don't know what any of the commands are, but there's something you can do to dump memory out in this mode. Ah, such a tiger. This is the slowest VM. This is a really bad VM. I should be using a different VM. Alright, so we have commands. I think I can just search this for disassemble. Ah, there's a U command for unassembly. So I think all I was doing here is something like U, and then a start address and an end address, and then it beach balls for a bit, and then I get some text here. I get a lot of text here. So that was the first 4 kilobytes of ROM. And then I can just like literally copy and paste out of this dialog box. So easy solution, but yeah, this does have like a logging feature, but for some reason I was having trouble with that, and just plain old copy and paste ended up working. All right, so that's the end result. Let's take a look at the patch and see what that actually involved. And where did I put that? that is in my, oh, it's in my Dropbox, which is over here. LC87 debugger. Oh, yeah. That's just a copy of, oh, no, here we go, experiments. Yeah, here we go. These are my reverse engineering notes from earlier. And so I've got copies of the software we were just looking at in IDA. I think these might be my IDA databases from earlier too. Yeah, that's my IDA database. So if we wanted to look at my earlier reverse engineering project or progress, we could, but I think the most interesting part of this is actually in my earlier experiments, these knockers where I was trying to like knock on the one-wire debugging port with various sequences. So these are like Arduino sketches. But this is the one that actually worked, this patch to the Great Vet code called B, the TCB87 Type-C dongle, sort of. So I think that's what we want. Oh, do I have Sublime Text on here? I don't. It's annoying. Oh, text edit. Yeah, the mouse is not great even outside the VM, so I think I might blame this wireless mouse. I think I just need to learn not to use wireless around here when it matters. Alright, so this is a patch to the kind of official / experimental firmware for the Great Vet. And so it's an ARM. It's based on this open source library for that chip called libopencm3 for Cortex M3 is the ARM core, and so it's an open source library that helps out with that. And then I just do terrible things in here. So this include file is just like a binary blob that has the code I'm debugging. In this case, I think it's the dongle itself. This actually needs 2 binary blobs because this, before it can actually be a debug dongle, the first thing that happens with the RD87 app is it actually needs to put the firmware on the dongle itself. So in order to, I mean, that's basically a process that you have to some extent emulate. So what I ended up doing was just emulating that and having it store the firmware in like a RAM buffer. And I think later I added something where I had the firmware built into the flash so that it could skip a step. But in either case, either the firmware is kind of baked into the Great Vet image, or you install the firmware using the usual like firmware update thing, but emulated. And then you end up with this image of the firmware, and the RD87 debugger asks you like questions about it, like a checksum or like the version number. So you have to at least be prepared to answer those questions, even if you don't have the full image, or it'll just assume that you're out of date and try to reflash you, and it'll just get stuck in a loop. So I think everything I had to add was at this USB vendor request stage. And if you're not familiar with the USB protocol, it's got many different layers to it. It has this low electrical layer with packets on top of that. And the packets are very chatty. They're always asking, like, do you have any packets on this buffer? Would you accept a packet on this buffer? Oh, here's a packet. But then above that, you have these transfers that occur on endpoints that look a lot like serial ports or pipes. And to a large extent, those are application defined. But there's still a higher level yet transfer scheme where you have kind of a request and a reply based on endpoint number 0. And so those are these control requests. And I think everything we're doing here happens on the control requests, which means that we don't really have to worry about like a byte stream or like framing or packet formats as much. We know there's kind of a scaffolding that involves a packet with an 8-byte header that encodes a couple of parameters that could be up to 16 bits, and then an optional block of data that's after the header. So this setup stage that we're handling in this firmware is actually that 8-byte header that's shared among a bunch of other types of standard USB requests. What is this doing here? So this is actually just part of the request. I think the real interesting part of it here is, let's open this up in a better text editor. This is ridiculous. This is the binary data for the firmware image. I think that's the last thing that's interesting in this patch. Oh, no, it really isn't. Okay, this will be more tolerable if we do a little bit of groundwork and make sure that we have a checkout of this repository and a real text editor. Let's just grab a copy of Sublime Text on here. Oh, and why is this so slow? Oh man, when I was just helping my neighbor with her computer, it was being super slow too, and so now I'm like, oh no, technology is just all terrible. Geez, why does Spotify need a half a gigabyte? Man, maybe it's just the zooming in is actually ridiculously slow in combination with some of the other stuff I'm doing. So maybe I'll just have to find other ways of magnifying the screen. I have a feeling this computer would maybe be slightly faster if it wasn't also compressing the screen and sending it over the network. Oh, in fact, I wonder if that's related. Like maybe having a VM window open is causing it to do that, because I don't know. Like when the VM updates the screen, it's going to have a rectangle where it says, you know, this is the area that changed. The graphics driver, in collaboration with the window manager and whatever other applications are running, they'll calculate the dirty rectangle on the screen and tell the driver what's changed. And then in the VM, it does its best to communicate that to the operating system, you know, using OpenGL and like a partial buffer update and that kind of thing. But depending on the video driver, like that might just get thrown away immediately. And then when the streaming, so I'm using like AirPlay mirroring to stream this, and so that might just end up having to compress all that video at like 60 frames a second just because it doesn't know that it hasn't changed. So I'm going to hide that and see if the computer is less completely overwhelmed. So I think I already downloaded that, yeah. Do I already have Git on here? I do. And do I have GreatFet? Oh, I already have the GreatFet code also. Is it up to date? It is not patched. Let's see if it's up to date. Not quite. Close though. So let's patch it, and then just take a look at the patched code, because that'll be easier than reading the patch file. Where is that file? Dropbox. All right. Succeeded with some fuzz. Isn't that great? Fuzz 1. I think it'll be fine. So, and now if we do a git diff, it's giving us pretty much the same thing, but git is formatting it a little nicer. And if we do git status, so that's what we're looking at. And now we should actually be able to open it up in a less simple and hard to use text editor. Mostly it's just I'm used to Sublime Text. There's nothing really that wrong with TextEdit, but this is what I'm used to, so it'll be less jarring. Although it will ask me to register because I'm not going to go through with copying my license key in there while I'm streaming. Anyway. Oh man, maybe this computer is having some disk slowness. What's that spotlight? Yeah, I don't know. For all I know, the VM is like installing Windows updates right now or something. I've been trying other text editors occasionally. Like I tried Atom right after it came out, but didn't really like it. I don't really know why. I think I was just, it seemed pretty equivalent to Sublime Text and didn't really seem, and it didn't run quite as well and was missing some of the features I liked. I think before Sublime Text, I was really more into like Emacs and VI and that kind of stuff. I usually used Emacs for like real coding sessions, and then VI for when I didn't feel like waiting for Emacs to load. Man. We're still verifying this application. Doing some crypto on all its pages, I guess. I still have not actually researched how the new, I guess this is from macOS Sierra. I mean, I think it's based on stuff that's been around for a while, but yeah, I really need to catch up on all the latest in macOS application signing, because I really should know more about how this works under the hood than I currently do. I think the last time I looked into the signing was just, like, I needed to just disassemble the dock for some reason, and so I had to figure out how to get around that for the moment. Oh man, well finally. That looked like it was some kind of network timeout that was just happening, but anyway, Sublime Text, yay. Do I have Subble in my path? No. Okay, let's just do this. Why is this beach balling? All right. Fewer beach balls. Yeah, maybe, I mean, it'll be nice, like, once I upgrade the streaming machine, like, in the future, I might have something with more HDMI inputs, and then I can use an HDMI input for this instead of taxing this machine with more compression duties. All right, so we don't really care about the host code right now, because all we're going to do is take the kind of scaffolding firmware and kind of hack in some new commands. So this is the file we care about. And this is this USB 0 vendor request is the main entry point for these endpoint 0 requests. Oh, and the indentation here is kind of messed up. I must have edited this with something with bad tabs before. Anyway, besides that embarrassment, you can see that I have found a couple of the critical endpoint 0 control requests that the software is expecting. So, you know, if it's request number hex F0, F2, you know, this seems to be a write to some kind of memory, seems to be some kind of command, some kind of read. So it's important to at least like have the firmware know like whether to expect a data stage. Is if you have the firmware, you know, by default, if you just have like some firmware that is just like some open USB example application or something that doesn't have a special handler for a USB request. In fact, you can see right up here, the default response for this handler is a stall. So what that means is the driver tries to issue the command, then at a hardware level, the microcontroller gets this buffer, which then raises an interrupt, and then this function gets called, and the function gets an opportunity to say, you know, is this command legit or not? And if it isn't, then the driver can set a flag in the hardware that then says, actually, something went wrong, just tell the driver to give up on this endpoint. And so when that happens to endpoint 0, you end up with, you know, the driver sees a failed command, and then the hardware on the other end, the host controller, then has to, you know, has to kind of take that error into account and propagate that error on. And then the driver has to explicitly clear that error with another command, and it has to do like a clear feature flag, you know, clear the endpoint stall. So, you know, it's this whole error and error recovery process, and typically a driver won't really like that, and it'll just stop loading at that point. It'll take the hint. But in this case, we want the driver to continue, even if we don't actually have everything implemented, even if we're just kind of stubbing things out. So we can't stall. So we have to go through with the request. But for that to happen correctly, we have to, you know, there's like a state machine that each of these endpoint 0 requests kind of follows in multiple stages, where there's this header, the 8-byte setup, and then there's a data stage, and then there's an acknowledgement after that. And for that to succeed properly, you know, there are probably ways of faking that out. Like if you were writing a device specifically to be like a yes man, like, you know, it does anything you want and just, you know, says, oh, I totally did that, even though it totally didn't. You know, I can imagine doing something like that as like a special purpose USB stack possibly. But in a normal USB stack, these state machines are only going to proceed properly if you know the proper transfer direction. So we have to at least know, like, you know, okay, this command seems to be writing some data. This command doesn't have any data stage, it's just the command itself. I forget what this flag was, step flag. Yeah, maybe that was something I was... Oh, that's single stepping. Okay, step, yes. So I guess you can see notes from different stages in the reverse engineering here. So I had this command, F2. I documented that it was, you know, the kind of type of USB command it is. It's just doesn't have a data stage. It's just a command. It's a vendor out. But then down here it's documented as a single step. So I don't think that's actually necessary. Like, I think I started implementing some more of this to see if I could get a little further, but that's not really necessary. So then here's a status read. Like, it looks like this is a read that returns a 3-byte packet that is a little different depending on the context here. And so I think a lot of this was just going step by step and kind of trying to get a little further and then seeing what the function that was failing was expecting in the disassembly. So right here, like, I think this was actually being checked against some table of different versions that RD87 expected. And so RD87 would issue this command 1E, or this command F1 with a subcommand 1E, and then expect to get a version code. And so I looked in the table where it was expecting to find this and found that. So, and then the scaffolding around this is largely going to depend on what the device is. So in this case, it's actually a pretty nice, spacious, like, ARM machine with, you know, a nice modern C compiler and pretty nicely designed open source C libraries. So we get to do this asynchronous I/O, and this is going to be an interrupt handler, and the interrupt handler gets to make a decision about what to do next and then schedule the next block of I/O. So the thing that we end up with on the Python side might be a little bit different, where we have an option to kind of script experiments in a more procedural way, but this is probably going to look more like creating a Python class that implements similar kind of event responders here. And then down here you can just see kind of the glue that connects this to the rest of the USB stack and generates serial numbers, GSG for Great Scott Gadgets, initialization, and then finally a main program. The firmware for this project is pretty, it still needs a lot of fleshing out, but this and a lot of things that are based on libopencm3 just feel so much nicer to work with than the usual stuff that you see in like silicon vendor examples, because I think there's a little bit less friction between the examples and the open source tool chains. You can write stuff where the example code is maybe using the tool chains a little bit more directly and not just kind of piling layers of stuff on top of them. All right. So I don't think we necessarily need to worry about compiling this. I think we can just use this code for reference. I think maybe the next thing to look at is just to see with the Facedancer, like what does it take to make a brand new kind of thing with that? Like where do we start writing code? Because I've used it at other levels of abstraction, but haven't actually quite done this yet before, so this will be a new experience. And that is not the Facedancer repository. Facedancer is in this GoodFet repository. And actually, before we go much further, I think I might also try to find that Sublime Text symlink, because I'm going to be annoyed without it. Yeah. Actually, I think I have a writable bin directory here. Yeah. Okay, so now I should just be able to do something like this. Firmware, and let's just take a look at that firmware. All right. So also, if I remember right, I think there were two different frameworks. Like there might have been kind of a transition from an old thing to a new thing. Oh, actually, firmware is not what we want, because the way that the Facedancer works, most of the work is not actually done on the microcontroller, it's done in the Python code. So we want the Python code, which is client. Now I don't know why Subble is opening 2 copies of every window I ask it for. It's another quirk. All right, so this is nice. So now we have libraries here. No, that's not the libraries. This is a makefile for HIT API, which is not relevant right now. So some Facedancer tools, some other GoodFet related tools. Where's the, I want to find the actual stuff behind this, so like the USB implementations. We've got these. This is a USB endpoint. It's an implementation, like an emulation of an FTDI adapter, an emulation of a keyboard. I think these were the older. So I think this is like the classic or like original framework or whatever. So I think USB here is just kind of USB definitions, and then we have something specific to that Maxim USB controller chip that's in the Facedancer. We have register definitions for it in Python. And then we have, yeah, there's kind of a mix here of stuff that's like devices and stuff that's like USB framework. But here's, for example, something for implementing USB mass storage devices. So this subclass is USB class because presumably that's a way of helping this attach to the device. Class is what USB would use to pair devices and drivers in a standard way. So let's see if that's something we want to subclass from or not. Maybe. I don't know. Let's see. Yeah, okay, so there's a separate thing. There's a USB vendor thing, which, because the thing that we're implementing is more like this FTDI device. It's not based on anything standard in the USB spec that's being extended. It just uses the low levels of the USB protocols, and then on top of that it says, oh, this is a vendor-specific device. My driver just wants raw access to whatever's underneath. So it seems like we should do something like this, and subclass USB vendor, and then this is looking nice. It looks like there's already a lot of infrastructure in here, and we have an opportunity, sort of like we had those if statements in the other firmware, to look for particular commands like these, like F1 and all that. It looks like we can put those in this table and have functions that handle those vendor-specific requests in Python. And so this is doing something similar using some presumably reverse-engineered details about how to talk to an FTDI serial chip. Okay, and then there's another class for a particular interface. Let's see how those two are connected to each other. So for transmitting, this is sending, so it looks like these are just control requests. Let's maybe try to find the name of this interface class. Okay, so there's another thing down here. Oh, okay. I misunderstood. This FTDI vendor thing is not a vendor-specific device. It's a vendor-specific command handler, which is part of a device. So just if you look at this, this is then the kind of glue that brings all the different aspects of the device together. So this looks like all the details that would go into the USB descriptors. So the little packets that are read using standard requests to figure out what driver to load and figure out how to represent this to the user. And this seems to be packing all of that into the binary descriptor format automatically for us, which is nice. And then this is a configuration descriptor which bundles together endpoints. We might be able to just do without all of that, since I don't think I think the RD87 stuff that we're trying to emulate, I think it only cares about these vendor-specific control requests. I don't think it cares about any of the rest of this. Oh, so this, there's a good question in chat about whether this, like what the context is for this FTDI device. And this isn't a driver for the FTDI. This is actually an emulation of the FTDI. So the idea with this is, by using this Python module, you can program one of these Facedancer boards to pretend to be an FTDI chip. And so in that case, there's actually multiple FTDI chips going on. There's a real FTDI chip that you're using to talk to this microcontroller. But then the combination of this micro and this USB interface and your Python script, those all work together to emulate another FTDI device, which you can then kind of mess with to try to find security issues, or to try to explore potential add-ons for the hardware, or it's kind of like a research platform where it lets you color outside the lines even if the thing that you're working with is normally stuck inside of a piece of silicon that you can't easily change. All right. So it looks like the first step here is to just make a copy of this, or start with something similar and just make a USB, or make a Python module for the kind of RD87 device. And then we'll also need like a main program to run. Let's see what that looks like for the FTDI. So that's pretty straightforward. It just this good fet serial port is how we're talking to the Facedancer. So in this case, this particular style of Python is just using the main program as kind of a configuration file for, how to talk to stuff. I mean, this in combination with environment variables. But the actual stuff that we care about is being done inside this class, the USB FTDI device. All right, so let's just start with making copies of those files to be templates, since that's the nice, easy way to do this. So where am I? Let's make sure we have a recent Git repo to work with first. All right, cool. So we'll need something like Facedancer FTDI.py, which is the entry point. So we'll call that Facedancer RD87. And then we'll also need something like that, what was it called? USB FTDI.py. And so the convention here seems to be USB just for all the classes related to USB, because this directory is shared with everything else GoodFet related. And then we'll just call that, I think to have a little bit more context than just RD87, maybe I was going to use the same name as the VM, which I think was Stanyo RD87, but I don't know if I want to be typing that all the time, so maybe we'll just call it RD87 over here. Sure. That's what we'll call it. Lowercase and uppercase in harmony. So keep that around for reference, but mostly we'll be over here on the new code. So this overall script, this Facedancer FTDI to RD87, this will just be a straightforward rename. This will do exactly the same thing. We probably won't need to customize it much past this, but we need something that's like a similar scaffolding here. I think everything else is, import from that module also. So that's I think all we need there. And then for the other one, I'll just delete most of that and use it as a starting point. So over here, this is going to actually be totally different. It won't be about FTDIs anymore. This will be about except that's not called the RD87, it's the TCB87. All right. The all-important comment for future generations. And all of those imports are good. We'll hold on to those. I don't know what util is for. Let's check that out just to see if I could delete that. Bytes as hex. Sure. I'll delete that for now because I don't think I need that. All right. And we actually want this to be that a slightly more descriptive name, because this isn't like the device and it isn't the entire vendor, it's just a collection of commands. But let's just empty out this list for now, because we don't want any of these. I don't know what this will do when you call a command that isn't in that list, but I'm sure we'll find out. We could also check the base class. That might be nice to see what it has built in. Presumably that's where the lookup code is. Yeah, or maybe it's in, I guess somebody else is reading this request handlers list. I can never actually remember the global search and replace keyboard combination in this. Shift command, huh? Oh, and then of course I find the wrong thing. I actually wanted to search for request handlers. A lot of people setting request handlers. Okay, this is where we're calling get. So it looks like there's most of that in this USB device file. Generic device. Completely generic. Okay, interesting. So, like, we don't want to override these. How are the subclasses handling that? What was in here? Because we really don't want to override the default chapter 9 requests necessarily, right? Like, get status and like set configuration, like those are fine with this particular implementation. So what are we doing there? If we go back to the FTDI, it doesn't look like they're calling the superclass. Maybe they're just overriding that unintentionally. Huh. What about the keyboard? I mean, maybe the FTDI specifically has some reason to override that entire array. I mean, the keyboard doesn't have anything vendor specific, so I guess that's not a good example. Serial, maybe? And this is even weirder. So now this USB vendor here. Oh, you know what? Maybe I'm just confusing USB device and USB vendor, because maybe USB device has one that is actually totally separate. So there's like a USB device request handlers, and then maybe this calls out to vendor if it detects the vendor specific flag in the, okay, handle request. This seems like the function we want. So yeah, so there's every USB request includes a little bit mask that indicates the destination as far as the protocol is concerned. So you can direct the requests to the endpoint, like the virtual pipe, or to the class, which is like what standard the device respects, or you can just say it's vendor specific. So it looks like it's using those bits to figure out what lookup to use. So that means that this isn't actually a problem. Like, this doesn't need to preserve the standard request handlers. It's only responsible for the vendor specific requests. Which does mean that if the device, like, I don't know, when I'm writing USB code, I often try not to take the spec too literally when I'm writing frameworks, because a lot of devices don't follow the spec. And so, for example, with this particular implementation, if I came across a device I wanted to emulate where there was something that for all practical purposes was vendor specific, but it wasn't coded as a vendor specific request, then I would have to kind of break this framework a little bit to accommodate that. But I think this is fine. We'll find out later. So then this interface is, I think in the USB, I think this represents a USB interface, which is a collection of pipes, like those endpoints that represent some bit of functionality. So maybe like an audio interface or a human interface, human input interface. And in this case, it's a collection of endpoints. Can I just omit this entirely? Because I don't think this device needs any endpoints other than 0. I think I can just have this be an empty list. Let's try that. And in that case, just remove all of this stuff. what? I'm just realizing that I've been calling this thing RD87 when actually it should be TCB87. So let me rename that before I get any further into this. I'm sure everybody in chat's been screaming at me about that. Alright, I think this text editor will be fine if I just close these. Okay. Now back to the other file, TCB87. Okay, so we don't need that. I'm going to try doing this without any interfaces, just the default endpoint 0, which doesn't need a descriptor because it's always implied. And I really don't care about the string descriptor, but whatever. Alright, so then, what is Max USB app? I assume that comes from USB. I don't know where this comes from. I'm going to look this up. Oh, that's a parameter. Okay. So whoever sets this up in main set up the Max USB chip and all that. Alright, so the rest of this, delete some of these inapplicable comments and put in the right vendor and product ID. So this is the stuff that we're going to get from what the VM, or sorry, what the software in the VM is expecting. Oh, RD87 I think is remote debugger for the TCB87 processors, or sorry, the LC87 processors. So I think, so many acronyms. I don't know where the 87 comes from. Maybe that's like the year it was invented in or something. Or maybe it's based on some other part number from ages ago. Anyway, I was looking for a thing. I think TCB87 is target control board, so that's the actual dongle. But then RD87 is remote debugger. Yeah, Sanyo LC87 is this the package on here. Okay, driver, and in the setup information we should be able to see the vendor and product IDs that we can pilfer. Yeah, these right here. So this is just the way Windows always encodes IDs for like USB and PCI devices. It's hexadecimal like we'd expect. It just kind of has this weird like underscore or ampersand encoding thing. But what we want is OAC3 1211. Let's hide this again. Go back here. Great, so now we can make our thing. And I don't think the driver is going to care about the revision or the actual name or anything else. So we can just put in whatever we want here. I don't think any of that matters. We do need to give it an object that actually exists here. All right, so I think that looks like it might run. Let's give it a shot. All right. Unplug that for now. Need a different USB cable. Oh, and I think there was also a question about the different kinds of, like the TCB87, like, you know, type A, B, C, etc. I don't think that those were necessarily like different versions of the, like, you know, I don't think they would have like sold those as different debug products. I think those were just designed at different points along the product lifespan for different processors. So I think, and I've been focusing on the type C because that one seems to be intended for the processors of the generation that these tablets use. I think that was, you know, so I think they had like a USB microcontroller and then a newer I think they had an 8-bit microcontroller without USB, and then a newer 8-bit microcontroller with, you know, still the same 3-wire debugging interface, but maybe other features, maybe more memory or something. And then they had their, I think at the same time they released one with USB and with 1-wire debugging. And then I think that's the last of this generation. I think after that people just moved to 32-bit. Because, you know, 8-bit microcontrollers with USB are kind of a niche product at this point. They had a little run, but for the most part, that, like, if you're an 8-bit microcontroller with USB, that, like, bookends, like, what years you existed pretty closely. All right. So we want to connect that not to Windows. We connect that to the Mac. And just talk to it with the good FET software. So I think what we want is a serial port. Oh man, which one of those was us? I think it was the one ending in NX, just from memory. Yeah. Okay. Oh, geez. Here we go. So I think then I want to set this good FET environment variable. And let's actually get in the right directory. Facedancer TCB87. So it looks to be running. So it's not going to do much, but it should appear to be the right kind of device. So now we want to plug the other side of this thing into our VM and just see what the driver starts trying to do to it. And I imagine that the driver, like the actual kernel mode driver proper that Windows installed, isn't going to want to do much because it's just this generic pass-through driver. So this might work just fine even without writing like any code in this device. We might just have it connect. But then I imagine once we actually run the debugger, it'll start hitting unimplemented functionality. So another USB cable. I didn't get that annoying pop-up this time. I don't seem to have gotten a USB device. Let's restart this. It's also possible this is some kind of problem with either my Facedancer or the cable or the USB hub port. So let me try exchanging a few of those objects. And first just plug in a different Facedancer. Beep, 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 beep. TCB, yeah, okay. Interesting. Don't know what it means by that, unless perhaps the firmware on this board is not awesome. Or maybe that's just the kind of bug that goes away if you run it again. Let's see if I'm seeing anything in IO Registry Explorer. We could just be hitting more weirdness from having both sides of the GoodFet or the Facedancer plugged into the same USB hub, in which case I might just grab a longer USB cable and plug it into a different port. We want IO USB. Don't see it. There's hit device. Oh, Yeah, I don't think that's showing up. I mean, you can try unplugging and replugging, but I don't think that's showing up. Yeah. I'm going to try the debugging tactic from before and just swap these two USB wires just in case one of them is going somewhere ineffective. And that looks the same. Looks like getting out of sync with the firmware on there. Oh. Well, now it seems to be communicating. So, that's suspicious. Maybe I will do that thing where I have a less sketchy USB setup and I have one of these going more directly to the computer and the other one with a cable that is nicer, maybe. I'm gonna grab some USB doodads. I will be right back. And in the meantime, have a full screen Tuco cam. Also take this opportunity to have a USB analyzer. Hey, cat. And try having the test and debug tools attached to a USB hub, but not the actual device. These USB hubs are, they're definitely not passive devices. Like if you have anything strange going on with USB with like power or timing or whatever, it's certainly possible the hub is involved. Which isn't to say that you shouldn't use hubs. I mean, I've got hubs all over the place. Just always be a little suspicious of them. If you really want some horror stories about hubs, read about what happens when you have like isochronous transfers to full speed devices on a high speed hub. It's just, ugh. It's taken, I think Linux took like years and years and years to get that stuff right in their drivers. The Macs under the desk certainly have their fans going. So in this case, this analyzer itself, like its traffic is going to be kind of mixed in with a bunch of other stuff on the hub, but the stuff it's analyzing will be pretty clean. Alright, so as another baseline test, let's just pull up the USB analyzer and run the programmed kind of Great Fet hack and just watch it go through. And then we should be able to see part of that happen with our work in progress Facedancer version of that. And we should be able to see where it's failing. Let's see. Try to use the homemade Facedancer as much as possible, because that's what I want to be showing in the video. That's the Facedancer being a generic FTDI thing. And here's the USB analyzer, completely idle. Well, it knows that like electrically there's something plugged in now, but and need a micro USB cable. Alright, so if I plug this in, we should see it enumerate, and we should be able to connect it to the VM. This is kind of chatty. I actually want this to be recording a little bit less detail. Yeah, I can have it, well, you know, I was going to suppress all the startup frames, but I think these are only showing up separately like this because there's something weird about them. Beach ball party. Huh. Let's just try that again. Disconnect. I think I have this USB analyzer set up kind of weirdly because I was doing something really unusual with it last time I was using it. So I think I might have turned off the auto detect for speed or something like that. Let me see if I can get that back to normal. Oh, stop capturing. Oh, this computer is still being so sluggish. Well, that's pretty normal. also possible I grabbed a cable that's just too long. Now, let's see if this shows up in the VM, regardless of what the software says about it. Now it's plugged in. Maybe it's just a bad USB cable. Could it be? Yeah, I don't see the GreatFET device. I do have it plugged in on the correct side. Alright, I'm just gonna swap USB cables. Maybe this one is not any good. Ah, yes, USB Folly Theater. We try to make the data flow at 12 megabits and often fail. This cable is more reputable. Thicker insulation, doesn't look like it's trying too hard. Ah, yes. Much better with a better cable. I will connect my Sanyo GreatFET to Windows. Bong bong. Alright, maybe that's why my analyzer was picking up a bunch of corrupted packets, because the cable was dumb. I'm going to sacrifice that cable. How should we sacrifice this cable? This is clearly a bad cable. It's clearly causing badness. It says it's USB high-speed certified. Look at that. Come on. Are we servo AF? Oh, camera, you're servo AF. Maybe if I compliment it enough, it'll focus. There we go. Yeah. Shielded. So what is actually in this that makes it so bad? Seems pretty typical. It might just be too long. It might just be not enough wire. I mean, it's not very gaugey in there. Anyway. Bye-bye power cable. Don't want anything, or bye. Would have been better if it was a power-only cable, but it's like I don't even need a charge cable that goes to full-size, like USB-A. I only use that for stuff like my USB analyzer and USB hubs and my oscilloscope where I actually care. So this seems better. Let's see if we can get a clean trace from the top with the GreatFET. So back to the computador. So the Great Fit's attached right now and just not saying much, but I'm going to unplug it and replug it. Hi, Windows. And VMware is replugging it. So that was pretty smooth, actually. So this is pretty typical USB kind of chit-chat getting the device started. The electrical negotiation, and the device addressing, and then the kind of interrogation as the operating system asks for all those descriptors. And I think we can take a quick look at some of those. And should be able to see the contents. Oh, that one isn't actually a string. That one's like a language table. Great Scott Gadgets. That's some kind of serial number. Anyway, this is all going to trace back to the kind of boilerplate code that we mostly glossed over in that USB device Python class. But all of, like when it gets one of these get string descriptor requests, this is one of those USB chapter 9, endpoint 0 control commands that we were talking about earlier, with a setup stage, and then a data stage, and an acknowledgement stage. So the setup packet is really what we have to process anytime we're handling one of these USB requests. And really, I should bring up the kind of mother document here, because if you're working with USB setup, you should really be aware of the Chapter 9 USB spec. I think maybe the best place to get this might still be USB 1.1, because it's smaller and a little easier. Oops. A little easier to trudge through. So I'm just searching for USB 1.1 spec, and I think that looks like a legit link, but let's check it out. I mean, the proper place to download this stuff from is like the USB IF, but it's often harder to find the older versions. And not that you shouldn't read like the USB 3 spec, but it's just going to have, because it's one of these things that is very much prioritizing backwards compatibility, the more recent the spec is, the bigger it is, because it just includes compatibility with all the older stuff. So a lot of this is not relevant, but we're looking for Chapter 9, which is often just called by that name. It's kind of famously described as the Chapter 9 specification. But this is what tells you how to be a USB device. So above the electrical layer, above where you're getting these packets that include little fragments of data and little headers, this specifies how you communicate with the driver and how you actually use these little primitives that are available to you to build a framework for your particular kind of device and your particular driver to communicate with each other. So that's pretty much what USB is. It's kind of like a little, like a construction kit for ways of communicating between a driver and a piece of hardware. And then it provides these kind of low-level bits, but then other specs like, for example, if you're making something that you want to have firmware update capabilities, then there's another spec, USB DFU, for device firmware update. And in addition to whatever else your device is doing over USB, if you also support that spec, then you can use standard firmware update tools. Or if you support the USB communication device spec, then your device, which might otherwise have all sorts of crazy stuff going on, could also be a serial port. And I like how that's gotten much easier for people to access now that, for example, the teensy devices, you can just like pick something from a menu in the Arduino IDE, and that gives you a device that's configured for something different. But under the hood, the way that works is through these USB descriptors. When you pick, like, I want this to be human interface plus MIDI, then that's just loading a library that is already built with a descriptor in it that includes interfaces for both of those bits of functionality. So, a part of this that I actually wanted to check out first is in these USB device requests. So I expected this to be a hyperlink, but I guess that's what we get for old documents. 183. Okay. This is the document that describes how these little 8-bit or 8-byte packets that every USB device uses for pretty much every kind of initialization and control. Like, that's what these are. So, only 8 bytes. We've got a couple of 16-bit fields here, so the offsets don't go all the way to 7. But it's just like a very simple container for commands that you would send a device. And these commands would range from, here's a new bus address to take on, or clear an error that happened earlier, or reset everything, or, you know, it's usually not like, here's a new data packet to transmit. It's usually something that's less common than that. But, you know, some less sophisticated devices certainly might do most of their work through these kind of control transfers. They're not efficient really, but they're mandatory, so if you only want to support one kind of thing, then you could do everything with these. And so the first byte in each of these just kind of encodes, and I was alluding to this earlier with the different dictionaries in the Python Facedancer code, so different handlers depending on whether it was like a vendor-specific thing or a standard thing, and that's what this tells you. It very, very broad things like, is this from the device to host or host to device? What part of the stack owns this request? And then this is also kind of like a targeting thing, like, is this specific to, like if it's a class-specific request, for example, and then it belongs to the device, then it's actually referring to the class of the device. And so if it's like an audio class device or a vendor class device, then like a vendor class specific, a class specific, a vendor specific command directed at the device would mean something much different than, say, like a vendor-specific. I mean, vendor-specific is weird because you don't really care what's in here. It's just like a license to do anything you want. But where this is actually necessary is when it is like a class-specific or a standard request, because the class associated with the interface might be different than the class associated with the device. And for sure, if it's a composite device, it could have multiple interfaces with different classes. But I don't know, a lot of it does kind of boil down to more procedure than anything else, and a lot of the way people use USB is different than the way USB is designed. And, you know, USB is intended to, you know, like, I think I mentioned this earlier with some of my videos that touched on, like, USB human interface devices. The specification was just very open-ended, and it didn't really know what devices were going to be used for. And then once you actually start developing, a lot of what actually came out onto market was more driven by, like, what particular end user experiences you could direct the operating system into creating by programming your device in different ways. So people were less interested in the letter of the spec and more into how they could use this to kind of get Windows to do what they wanted. And there's certainly a lot of that. I mean, that's exactly what I'm doing here. I'm just trying to get the program to have the results I want. So other than that kind of tiny bit of envelope information, mostly what you've got here is an 8-bit request type and then some optional parameters. So these index and value things are really just generic 16-bit values that have assigned meanings when it comes to these standardized commands. But if you're doing a vendor-specific command, they're just 16 bits here and 16 bits there. You can use them for whatever. This length does actually have a defined meaning because a lot of the stack uses this to keep track of the next data stages in the command. And then when it does come to standard commands, there's a bunch of those that are defined in the original USB, USB 1.1 spec in Chapter 9. And these are the kinds of things that we've been seeing in the USB analyzer to get the device set up and ask for descriptors. But the stuff that we should start seeing for communicating with the debugger is all going to be on top of this, fitting into the same kind of rough framework, but not intending to be standardized at all. So here we're seeing same kind of stuff. Here's one of those setup packets, just like from the document, receiving some of the descriptors. And then these SOFs, those are, I was kind of on the fence about disabling them earlier because they're a bit noisy and we don't care about them in this case. But those are the periodic start of frame indicators that USB sends out as a time base. And so each of these happens every millisecond, basically. And the hardware on the other side, so like the hardware on the computer this is plugged into, is sending those out automatically. So this just indicates basically that time is passing. The analyzer is logging these, but they're not interesting. And I think that brings us up to the present. I don't think there's anything interesting here. So that confirms that the driver we're seeing isn't doing anything. It just, like, all the stuff we're seeing up here, that wasn't the driver, that was Windows. Windows asks for the descriptors and caches them, and then figures out what driver to load. This set configuration might be coming from the driver, because that's kind of an initialization task that usually happens after you know what driver, after the driver's been specifically requested. That kind of tells the device, like, stop being idle, start being your usual self. Configuration 0 is idle, and most devices only have a configuration 1 other than that. So this might indicate that, okay, Windows finished doing its thing and the driver is attached, but then it's just waiting for user space to do something. So let's do something. If we run, actually, let's get through the Explorer window over here. Definitely going to be debugging why this machine is so slow after this stream. I think it might just be some stuff running in the background that I can't really go into right now, because like VMware is trying to update or something. Maybe Windows inside the VM is also trying to update. Why? There we go. I thought it said this folder was empty before. Weird. Anyway, down at the bottom we should have our binary. Alright, well, we've got bunches more of these requests now. And, the decoder, or the analyzer, doesn't know how to decode them any further, but some of these just have the setup, which isn't shown in the default view, but you can expand it. So this is, for example, a control transfer that's just like a command with no data stage. But then here's a 6-byte packet, here's a 1-byte packet. And all of these, if you expand them, will have that 8-byte data stage that includes, come on, yeah. So this is like the vendor-specific request bit field in there. And then the if statements that we were seeing earlier with like the F1 and F2, that's the 2nd byte. So that indicates what this is doing. And so we can see a few of these, and so I think the 6-byte thing is like, get the status of the debugger, like is it done with the last command, is it busy, that kind of thing. So that's why we're seeing it being pulled really frequently. We should also see some larger blocks as it's actually reading memory. And there's also that thing I mentioned earlier where during initialization, it's not just saying hi to the device, it's also trying to see if it needs to upgrade its firmware. So that should actually be one of the first things we see. We can catch the beginning of this if we go up to, right after the kind of idle period ended. Yeah, so this is the first thing we saw. And, there's a varying degree, you might not necessarily need to decode all of what's going on in here. So some of this is curiosity and some of it's necessity. Because a lot of this, you're pretty well served just by kind of mimicking what's going on here. But it can also be helpful to think about what's going on. So here's an F2 command with no data stage. It's an in here, which is just an acknowledgement in this case, indicating that it's oh, actually, maybe I was wrong. Maybe that's a 3-byte data. No, this doesn't have a data stage because these last 2 bytes are the length. These 3 bytes are just an empty data packet. This is the first byte is just the low-level indication that this is a data packet, and then the next 2 bytes are the checksum on the packet. So this is just a very low-level way of saying that there's nothing there. So we see a bunch of that. I think maybe this big one here is related to reading back part of the firmware in order to see what's already there. Not sure why that would be 0 in this case. An easy way to tell it's an in as opposed to an out is by looking at the highest bit in this first byte, because that indicates the direction. So this is reading, and it read back this array of zeros. And here's another thing where, oh, now we've actually got a version string, which is behind the picture in picture. There we go. So this was another control request that was probably reading from the firmware memory to see if it needs to do an upgrade. And so you can see here the same setup, 8-byte packet. It's a vendor-specific request with this 1-byte code F4. And then these are some parameters, which we don't really know the meaning of, but I think these are related to the location and size of the memory block it's reading. And then this last word is the size in little endian. So I think this is reading 128 bytes. This parameter here looks like it might also be the size, but in big endian. This is also 80, but oriented differently. And since it's vendor specific, they're free to choose whatever endianness they want, or maybe that's an 8-byte parameter and this byte means something else and it just happens to be 0 right now. So this return value, this version is actually coming from like a baked-in buffer that I built into the GreatFet firmware that just has like a copy of the firmware that I pilfered from the RD87 distro itself. And that was just to avoid having to do this loop where it just keeps trying to reload it, because it needs to report this value eventually. It was easier slightly to bake it into the firmware than to actually implement the update process. And I think more than it being easier, it also doesn't require the RAM, because on this processor I had a lot more flash memory than RAM to work with. So if I didn't actually implement the update, so when it's doing the update I just ignore that data, but then when it reads back the firmware I just return something from flash memory that matches what it expects. So it never actually has to do the update, but if it did, it would be a no-op. You can also see this is another detail of the lower level aspects of the USB packet. At this endpoint 0 level, it's 128 bytes, but then when we actually start looking at the packets on the wire, because of the speed of the USB bus and the negotiation that we went through earlier, we know that each of these in packets on the wire can only actually hold 64 bytes. So at the lower level, kind of below the driver level mostly, but it sort of straddles the boundary of the driver and the hardware level, so it depends. Different parts of the stack are kind of responsible for this on different architectures. So like the driver on Windows, for example, would probably see this as a single 128 byte control transfer. But on the firmware side, the hardware only has a buffer set aside for 64 bytes. So you're going to get an interrupt at this point and have to kind of pump the state machine to deal with the next packet. So that's why, like, from a higher level point of view, writing USB drivers with something like the GoodFet or with libUSB, you can often do this thing where you just process like one thing at a time, like an entire control transfer. Whereas when you're writing firmware, that kind of thing, even though it seems simple, is actually not a great option, because it could require so much memory, or it could require putting these artificial limits on the size of these transfers that might otherwise have to be pretty large. For example, if you're updating the firmware, you might transfer the entire firmware in one control transfer, or you might transfer, an 8 kilobyte block. And that's actually a pretty good use of a control transfer. And at the driver side, like on the PC, you don't really want to have to worry about 64 bytes at a time. But at the hardware level, that's what's going on. So that's often another kind of mismatch you have to deal with when kind of working on the firmware versus the higher level sides of USB. Oh man, this analyzer is beach balling, probably because I have it zoomed in. But So we got some of the initial just kind of back and forth to establish versions, and then we've got some polling. And I think at some point this gets down to what I actually wanted, which is dumping the memory in the kind of fake target that isn't actually connected. But some of these, that was 23 bytes. Some of these are actually going to be kind of long, where it like fills its whole screen full of disassembly data. But we could spend all day debugging the nuances of this. We can get back on track and actually start trying to make this in Python now that the USB port is no longer causing trouble. All right, so let's stop capturing. All right, enough of that for now. Windows is sad. Abnormalities occurred in the USB communication. I was seeing this a lot. We'll probably see that a lot still. It likes to complain in that very vague way when anything goes wrong with the communications. And then it forces you to exit, so there's no like keeping it around, I guess. All right, getting a different USB cable. Oh yeah, we gotta readjust the Tuco cam. Thanks for the ping. I can get some Tuco face while I'm at it here. Tuco butt. That's probably the best I'm going to get at the moment. Alright, mini USB. Okay. So let's just try running the same experiment. Oops, this is a different thing. Alright, well, it's getting multiple addresses, which does not usually bode well. Like somebody's resetting it a bunch. Is it trying to attach? You know, so this seems a lot like the problem I was having earlier that I was trying to blame on having this plugged into the same hub. But now I'm starting to wonder if maybe this is just like a timeout kind of problem, like maybe I'm not communicating fast enough and it's causing this to keep readdressing and resetting the device. Just gonna swap the boards again just to rule out a hardware problem. Seen that before. And so far, that looks the same. Okay, maybe it's not a hardware problem. Which is good. I guess I like problems that aren't hardware problems, I guess. Software problems kind of suck too. Well, we happen to have the USB analyzer right here, so let's see what that says. I'm wondering if this might be something strange about the Facedancer on Mac or something like that. Like the FTDI drivers on Mac OS are particularly bad. So it's possible that running the Facedancer stuff on a Linux VM might help. see what the, let's hide the VM and see what the analyzer says. Because I could believe this being like a performance-related problem if this is at all related to the general slow state of this computer. Oh, there's a question about whether this could be a timing issue between the crystal on here and the crystal in the hub. I've never seen that in practice, actually. I'd be curious to see that kind of failure. Okay. Try doing a hot plug. Got some addresses. Yeah, it's just getting this packet and then timing out. Like, does it respond? Oh boy. Well, maybe I'm just having some setup problems that, like, I don't know if you want me to continue kind of fumbling through this, or if I should just end the stream and try to like debug this offline and then come back stronger. Because this is disappointing. I want to be coding this thing up and not trying to figure out why my computer is fighting against me right now. I mean, sometimes it's nice to document the failures, but it's, I think, also just gets to a point where it's more frustrating. There was an acknowledgement to that, but it's like right after the set address happened. I wonder if it's possible that my repository has some like junk in it that's breaking this. I thought we had a clean Git repo though. It looks pretty clean, except for the stuff we've just been doing to it. Well, maybe the first thing I will do is just take this VM that's been complaining for the upgrade and just let it finish, and then see if that just frees up some memory or something. I don't actually know how much CPU this machine keeps having to spend to encode screen updates. And I guess part of it is I tend to look at the CPU update or CPU usage when I'm not doing much on the screen. But oh, weird. There's an I/O registry explorer task using 30% CPU. What is that even for? And then it's not even still there. Oh, I guess it was sporadically using CPU. This graph isn't even updating smoothly. I mean, it's kind of acting like whatever it is that's using a bunch of CPU is kind of transient enough that it isn't staying hot in this list. Oh, VMX is coming back. Oh, yeah, maybe, okay, or maybe somehow I just scrolled past the VMware VMX that was just like, okay, so whatever the CPU usage is in the guest. Maybe this VM is trying to update itself. Oh, Windows 7. Yeah, I don't know. Maybe I'll just let this shut down and restart. Tuco, how's your nap? Alright, Windows shut down. Let VMware update. Like, I've tried to keep this machine pretty light so that it doesn't bog down while I'm doing demos. It seems like, I don't know, my main suspicion is the screen sharing over a network, because that involves this thing like compressing the screen, but it should be doing that mostly in hardware, so. You know, I'm still getting this set address loop. I'm not plugging it into the VM yet, but this is just trying to connect to Mac OS, and it's almost acting like this might just be an incompatibility, perhaps even something that's recently developed between Mac OS's USB stack and the Facedancer firmware, or the Facedancer client rather. So this might be something where, to actually do this bit of video, I end up needing to use not a VM, but a real Windows machine. Which I can do. I don't necessarily have the ability to do that during a stream super easily. But I guess just as one example, I mean, when I was originally putting together the Facedancer, I think I was having a similar problem, and instead of plugging into the Mac, I tried plugging it into this Chromebook. So, yeah, that may be one thing to try. Just swap this USB out. Oh, yeah, the wallpaper with Tuco on the keyboard was pretty good. Yeah, that was a pretty lucky photo. I get a lot of good photos of Tuco, though. He's super photogenic. So, actually, instead of plugging this into the laptop with the chat, I'm going to use a random Raspberry Pi, because that seems less likely to break things. Ow! That was a bolt under my foot. Hey, Tuco, how about you take this? It's better in your mouth than in my foot. Alright, random Raspberry. Super handy to have something Raspberry around for testing devices. Linux's USB stack is pretty unsurprising relative to other OSs. That looks better already. Like, I wasn't really watching this when I plugged it in, but let's try that again. Oh yeah, that looks normal. Let's watch that in the USB analyzer just for fun. So that's good and bad news. It means that I think I understand what's going on, but it also means that it seems like Facedancer is not super Mac friendly right now, which would be an interesting thing to debug on its own, but is also, oh, I was getting distracted. What am I looking for? Right, USB analyzer. Data center, right, that's what they call it. To me, a data center is not a USB analyzer, but whatever. But yeah, I might need to see if I can get this, like this demo machine switchable to Windows and then find some other way of streaming the screen over. Alright, so boring, start of frames. Here I'm unplugging it. Let's get the camera going just to have something else for reference. So there's the Facedancer, here's the Raspberry. In between is the USB analyzer connected to the Mac. That's all the good stuff. So one thing that's nice about this setup is we can use the USB analyzer to see what's going on as kind of a, it's just like a great, powerful tool for this where any USB device, any driver, it doesn't matter. You just put the hardware analyzer on there. But we are also getting the exact same data out here just on the terminal when we run the Facedancer program. So that means that if you can use Facedancer to create something that kind of gets the driver going in the direction you want it to go, now you've also got a log of all the activity that's been going on without having to, use some other separate hardware or software solution to get that log. Well, the next step in this really is to take this and plug it into Windows and watch RD87 do its thing. I do have a Windows machine I could plug it into, which is not equipped with video recording right now, if we just wanted to make progress. But I think it might be better actually to wrap up this stream for now and then do some work behind the scenes to get this working a little bit better, and then pick up on the next stream with the same kind of Facedancer stuff and the same code we were starting into already. But I think I need to get a Windows-based demo machine that doesn't suffer from whatever this glitch is, and then make some progress from there. It seems like Tuco might be in the mood for some fetch, though. Maybe we can finish up the stream with some of that today. Hey Tuco, I'm gonna go stop the other recorder so I don't fill up all the hard disks with Tuco fetch. Hey Tuco. Yeah, you just want to rub your face on everything. Yeah, already. So there's already some good suggestions in the stream about about recording the Windows machine, and yeah, I could probably do something similar with RDP. On the Mac that I've been using right now, so I've got the HDMI out giving me the kind of higher quality recording for later, but I can't really stream that because there are like a couple of seconds of lag on that. And I mean, there are ways around that. Like I could use a different HDMI recorder that doesn't have that lag, but I don't have that hardware here currently, and I would need to buy some other components to make that usable. Like upgrade that streaming machine finally. But yeah, I tried. So currently it's using like AirPlay screen mirroring, and I tried that and the Apple's VNC server. Because they actually have a pretty good built-in VNC implementation that seems to use JPEG compression and do like a fast pass, and then when things settle down, it gives you a higher quality encoding. So the VNC plus JPEG screen sharing on Mac was pretty good, but still lagged behind a lot when I had video or anything 3D opened, because it just, I was just not taking all the fast paths to get things encoded, and it wasn't really encoding video so much as it was just encoding whatever the latest frame happened to be. So it's more like you get a slideshow rather than you get a pipeline of frames. So the AirPlay stuff seems to avoid that because it actually like encodes an H.264 video on your GPU and then streams that over the network. So that works pretty well. I think the other thing that's nice is having it use the local screen and local GPU, whereas with RDP, I don't know if there's a good way to have RDP use the existing desktop session instead of creating a new desktop session that doesn't necessarily have access to your GPU. I think there might be a way around that though. Like some RDP clients have an option to connect to the console session. I just don't know if that works with the combination of versions of Windows I'm using right now. So I'll have to look into that. There's also the option of when I upgrade the streaming machine to something I can put more inputs into, and I can just have a lower latency HDMI input for recording and streaming. Juco, that's a hard one. I think it's under, there's like a ladder and a little carpet square or something. I think he's trying to dig it out. Oh, there's also a good suggestion. What if I just add the HDMI delay to everything else? I tried that too. One of the iterations of this setup before, so like right now I'm using these Blackmagic HDMI captures for the stream, which are really low latency, but then I'm using these Elgato capture devices for the recording, which you know, they're not amazing, but they're inexpensive and they don't require like a computer with fancy Thunderbolt or USB 3, so I can use any of my machines around here to record. And so I was originally trying to do the stream through those boxes also and just get all the latencies synchronized. But I ran into this problem where the latency changed depending on what the video mode the source was in. And at that time I was still trying to switch between different sources, some of which were 59 frames a second, some of which were 60. So I don't know, maybe now that I'm not trying to switch sources, I could get the latencies calibrated again. So I'll keep that option open. But it was pretty annoying last time I looked into it. I was trying to use OBS and add a delay that was calibrated just right, but it depended on seemingly a lot of things. Good cat, Tuka. Have we destroyed this USB cable enough? I mean, don't really want to light it on fire inside necessarily, but man, it'll actually keep. I mean, I'm not going to like throw it away. I have a whole bucket of, I think my label for it is partial cables or hackable cables, because I usually will like cut something in half to indicate that it doesn't necessarily work as intended, but then maybe use each half for something where it doesn't matter so much. I guess I could also just have a camera on the screen or something of that nature for, I mean, that's kind of what these HDMI grabbers are, just like an input device that gives me a nice stream, but I'm just running out of I/O ports and CPU cycles on that machine. And a camera would still use I/O ports and CPU cycles, but certainly much less than a full 1080p HDMI grabber. I definitely have some cameras even right now that, like there's I have cameras from my machine closet, and they usually do not stay synchronized because they're like motion JPEG over HTTP. So there's like this thing. Oh, and I've also got a camera. This is supposed to be my other mill, but I keep having to restart the process on there. Like it isn't. It's like MJPEG Streamer running on an embedded Linux thing. Not a Raspberry Pi, but something really similar to a Raspberry Pi. And the process keeps running, but the video stream stops. And if I kill the process and let it restart, it's fine. So I haven't debugged what's going on there yet, but it just is yet another way that things can break while I'm streaming. Oh Oh yeah, there's also a question about some magic HDMI-based clock sync, and for doing this in post, there certainly is. I mean, if I had like professional television studio gear here, I could use like SMPTE or SMPTE or however you say that. Like there's a standard for embedding time codes in a signal that looks a lot like audio, and then so you can pass that over audio equipment, or keep it in like a sub-channel that's synchronized with your video. So that would be really nice. The way that I synchronize stuff here for post-processing is just to mix the same audio into all my video streams. So I just have this flow where I have a couple of microphones and the computer inputs and whatever, and then Ableton mixes all those together and records them if I'm recording, and then the output from that just gets split off into all the video recorders so that I can synchronize them using that afterwards. And I thought, man, it would be really cool if I could do something like that, but with the live broadcast. So maybe write a plugin for OBS that would do like automatic buffer tweaking to get the different streams lined up using their respective audio. So that might be fun, like something that's much more, I guess it would be a project that would give me an excuse to get deep into OBS and start tinkering with the code in there, which could be fun. Yeah, I probably should just put in like some timed reboot on there. I just don't know how long it actually runs successfully, so I don't even know when to time the reboot so that the stream is going when I need it to be going. Tuco sure does fetch a lot before getting tired of it. I think he's getting slightly less enthusiastic about it. I might have to go soon anyway, because I'm just starting to realize that I'm actually super hungry, and that maybe eating a thing is something I should do today. I'd like a piece of toast between the two streams. Maybe I'll have something slightly more meal-like. I love you, Tuco. You still want to play fetch, or are you done? I think he still wants to play. Oh yeah, there's another good question, or good comment that I should just reboot before the stream, and that's totally true. I think I will do that when I'm streaming and I expect to use the camera in there. But so far, I have not done a stream where I'm actually machining something or 3D printing something on the stream, but that's something I want to get into, and I've been making sure my setup can handle that. I've got a little fisheye camera in the other mill, and another little webcam on the Type A 3D printer. And it's fun to watch the robots make progress. Yeah, maybe I should have 2 bits of toast. Yeah, really, I do tend to be better at feeding myself when I take Tuco's hints. And he's begging me for something to eat, and I'm like, oh yeah, actually food. Actually food exists. Let's have that. He just got startled because I think he heard a door open next door. Hey, Tuco. You want to fetch one more, and then we'll get some food? Do you see that one? There's a bolt there, but I think he's not sure which one it is. Like, I think it might have been an ambiguous situation. He still has trouble with situations where there are multiple bolts and he's not sure which one is his bolt. Then he'll just come back and be like, oh, I can't do this. Tuco, you found a bolt. Do you want one more, or does that mean you're done? Are you done, little guy? I want one more. One more? Oh, that's another great suggestion from Ben in the chat, that I have a 3D print going in the background while I'm doing another job and let them race. And that actually is pretty good. Actually, I want to print more of my little... I've been experimenting with whether I can make objects that use both PLA plastic and this plastic putty, Sculpey putty. And I've been experimenting to see if I can basically 3D print a mold and then like press Sculpey Putty into that mold and then like bake it together. And so I should 3D print some more molds for that. All right, I could do this all day. Hey, cat. All right, one more and then dinner. Yeah, I love this little cat. All right, Took. Let's say goodbye to the stream. All right, thanks everybody for another nice stream. We'll pick this up soon, and I'll try to give people some warning on Twitter. And if you're not already set up to get the notifications for when the stream goes live on YouTube, that's also a thing you can do if you want. But we'll be picking this up soon with hopefully a nicer Windows-based demo setup, and then we can get into writing some of this fake TCB87 code. So thanks. Have a great night, everyone. Extra bonus stream wherein I wrestle with Synergy to try to stop the recording. Yeah, VMs and Synergy definitely don't like each other right now. All right. Goodbye for reals this time. See you all soon.